As their name suggests, neural networks are inspired by biological neural networks, and vaguely emulate the way that we humans learn. The most basic form of a neural network, the perceptron, is analogous to the biological neuron of a brain. The perceptron is trained to receive inputs in the form of input nodes and transfer the appropriate output. Similar to how with neurons, the dendrite receives electrical signals, while the axon branches out to multiple axon terminals to send the appropriate signal. Many neurons form a biological network, similar to how a multi-layered perceptron forms a fully connected neural network. The emergence of a technique known as backpropagation, which we will discuss in a lot of depth later on, is what allowed neural networks to figure out patterns that are far too convoluted and far too complex for a human to extract. In this section, let's dive deeper into the workings of a perceptron, weights, and gradient descent. To conclude this entire course, we're going to end up making use of a neural network to predict steering angles for a car to drive on its own, according to which part of the track it's currently in. So it's really important that we get acquainted with the workings of a perceptron-based neural network. I will see you in there. Learning uses a variety of algorithms to describe and analyze data, learn from it, improve, and predict useful outcomes. Oftentimes, it is not enough to directly program a computer to perform a specific task. Tasks such as driving a car, speech recognition, and object detection are way too complex to just program, whereas a machine learning algorithm can learn and improve based on experience, interact with its environment, learn to detect and predict meaningful patterns to achieve desired results. The learning occurs between a learner and the environment. On that note, it's important to distinguish between supervised and unsupervised learning. Supervised learning is the most popular machine learning technique that acts as a guide to teach the algorithm what conclusions it should come up with. Supervised learning typically begins with a dataset that's associated with labeled features which define the meaning of our data, and finds patterns that can be applied to an analytics process. Another machine learning approach that occurs between the learner and its environment is unsupervised learning. In this case, all the learner gets as training is large datasets with no labels, and the learner's task is to process that data, find similarities and differences in the information provided, and act on that information without prior training. Let us first consider supervised learning. Consider the task of learning to classify handwritten digits. In such a case, the learner must figure out a rule for labeling a newly handwritten digit. On that basis, a supervised learning algorithm would process images of handwritten digits along with correct labels, which denote the number each image represents. What that will do is provide significant information that is missing in the newly inputted data, which don't have a label to which we can apply the learning expertise and predict that missing information. That is, the learner is initially being supervised as it is provided with extra information in the beginning, and then through convolutional neural networks learns the relationship between the handwritten images and their associated numbers, and applies that relationship to classify completely new images that the machine hasn't seen before. In essence, whatever dataset is presented to it, it will try and predict its value based on prior training with previously labeled datasets. In this course, we're mostly going to deal with supervised learning. That in supervised learning, the learner is trained and makes use of datasets associated with labeled features, which define the meaning of our data. That way, when it's introduced to newly inputted data, it's able to predict missing information based on established rule sets and patterns. In other words, in supervised learning, a learner is provided examples of certain inputs and outputs, and based on that training, given a new input, it's able to predict the corresponding outputs. In this lesson, we'll talk about linear regression, a supervised learning algorithm that allows us to make predictions based on linearly arranged datasets. For now, we'll look into an example of a simple linear regression model, which would model the relationship of a quantitative response variable and an explanatory variable. The response variable is the dependent variable whose value we want to explain and predict based on the values of the independent variable. More specifically, we'll look to establish a linear relationship between the price of the house with respect to its size. The price of the house will be dependent on the size, and as such, it will represent our response variable, whereas the size of the house is the independent variable whose values we're going to use to try and make predictions about the price. Accordingly, the size of the house is the input, and the output is what we're trying to predict, the price itself. We're currently given a set of data points which reflect the price of some houses based on their size, and for each house with a given size, it's given a price label. This small 400 square foot house is $210,000, and the larger 600 square foot house is about $480,000. What about the value of the 500 square foot house? Well, you could just eyeball it and estimate that it's somewhere over here, or even do some kind of interpolation to get the exact value, or we can draw the line that best fits our data. We're applying a linear function that best approximates the relationship between our two variables. This creates a predictive model for our data, showing trends in our data and can thereby predict values of new data, which were not initially labeled. This is known as linear regression. Thanks to the linear function that we established from our previously labeled data sets, if we're given new inputs, which don't have a label, we're able to predict and estimate the output based on where the y value falls on the regression line. That's one form of supervised learning, predicting the values of new data based on a linear regression, and it's important to note that realistically, data does not behave like a straight line. They are random x and y observations that, on average, may follow a linear pattern, which is why we use linear regression models to represent them. As such, the linear regression model also accounts for an error value. Our predictive model, through some learning rates, learns to minimize this error by updating its linear function until no further improvement is possible. Thanks to this linear function that we established from our labeled data sets, when we're given new inputs which don't have an output, it's able to predict the most accurate value based on where its value falls on the regression line. Linear regression is one of the most well-known and understood algorithms in machine learning. This actually segues into our next discussion, where we'll also learn how we can use lines to classify data among discrete classes. This is another form of supervised learning called classification, a very important concept in self-driving cars. Classification predictive modeling approximates a mapping function which predicts the class or category for a given observation. In the most simple terms, it takes some kind of input x and classifies it, maps it to some category. Generally, based on previous data sets, it would calculate the likelihood of something belonging to some class. The best way to get a broad sense of how classification works is to go through an example. Say we're a hospital which annually tests thousands of patients. It's our job, based on that person's condition, to determine whether or not they are likely to become diabetic. Let's suppose the examination contains information regarding two attributes, the person's blood sugar and their age. Generally speaking, high blood sugar normally indicates a resistance to insulin. Without insulin, a lot of sugar builds up in the bloodstream, leading to diabetes. As far as age goes, as someone gets older, generally speaking, they tend to exercise less, gain weight, increasing the risk of diabetes as well. Obviously, in diagnosis, a lot of other factors are considered like blood pressure, cholesterol levels, family history, etc. But for the sake of our model, and keeping things simple, we'll assume that the higher your blood sugar and the older you are, the more likely you are to become diabetic. Suppose one person has blood sugar levels of 2 millimoles per liter and is 20 years old. This person is young and their blood sugar levels are relatively low, and thus unlikely that they would be diabetic. They're in good health. Another person is 60 years old with blood sugar levels of 11 millimoles per liter. Obviously, this person is relatively older with a very high blood sugar, so we'll assume it's very likely that they are diabetic. Finally, there is another person who's 45 years old with blood sugar levels of 5 millimoles per liter. Is this person likely to have the disease or not likely? This one's a bit of a question mark. We need some kind of predictive model which can predict the category, the class to which a person belongs in, based on this given input. The categories being, is that person likely to have the disease or not? We'll start by representing this predictive model inside of a two-dimensional Cartesian coordinate system. Blood glucose levels will traverse the vertical axis, which will range from 0 to 12 millimoles per liter, and age will traverse the horizontal axis, in our case simply ranging from 0 to 100 years. What we'll do now is plot the people we have so far. The first one will be plotted on the coordinates that denote 2 millimoles per liter of sugar and 20 years old, located in the bottom left of our coordinate space. The second person will be plotted on the coordinates denoting 11 millimoles per liter and 60 years old. Let's assume that we ended up testing both of our patients and actually found out that this person indeed did have diabetes and this person did not. Thus, we can assign each one a label, such that this applicant has the disease and this one does not. We'll denote not being diabetic as blue and actually having the disease as red. How does this determine whether or not the person who's 45 years old with 5 millimoles per liter of glucose level have diabetes or not? To which class do we classify this person? Is he likely to have the disease or not? Well, recall that since classification is a supervised form of learning, we need previously labeled datasets so that we can develop a model which is going to learn how to calculate the likelihood of a new patient belonging to some class. What you're seeing now, all of these points are actually patients who we ended up testing. We found out which ones were diabetic and which ones weren't. Anyone that didn't have it was labeled as blue, and anyone that did carry the disease is labeled red. Clearly there's a pattern in our data. The higher your age and blood sugar, the more likely you are to become diabetic. What about this person who's 45 years old, with sugar levels of 5 millimoles per liter? This person, unlike the others, we haven't actually tested them. They have not been labeled, but based on previous data, it can be confidently predicted that no, this person is not likely to have the disease. You can easily look and see that previous patients with similar blood sugar and age, whom we actually tested, are not diabetic. Thus, we can conclude that this person is likely not to be diabetic either. Now recall, we previously discussed how we can use lines to classify data among discrete classes. Well, simply enough, our data can be separated by a line. This line is represented by some linear equation. How do we obtain the equation of this line? Well, that's a much longer discussion that we'll leave for later. But essentially, there is a clear distinction that patients above the line are diabetic and patients below the line are not. That being said, based on this line, based on our predictive model, which was obtained thanks to previous data sets, we can effectively predict the probability of a new patient having diabetes. If, for example, someone has blood sugar levels of 4 millimoles per liter and is 55 years old, this is a new data set, and it's not labeled. We haven't actually tested this person, so we don't know. We need to use our linear model, which we obtained from previously labeled datasets to make a prediction. Clearly this coordinate is plotted below the line. It can then be confidently assumed that this person is not likely to be diabetic. In summary, what we're doing is first looking at previous datasets of patients who have already been labeled as having the disease or not, and based on that data, we can come up with a pattern, a predictive linear model, a line that best separates our data into discrete classes. Classification, in itself, is a very important concept in self-driving cars. Implementing an algorithm that's able to find this line with minimal error will be the entire focus of this section. Solving classification problems is essential in self-driving cars and can be used to classify whether an object crossing the road is a car, a pedestrian, a bicycle, or even identifying different traffic signs. We can use it to predict the value of new data which don't have a label based on their score. Let's kick things up a notch and relate all of this to the notion of perceptrons. The perceptron is the most basic form of a neural network that takes inspiration from the brain. The brain is a complex information processing device with incredible pattern recognition abilities. It's able to effortlessly process input from its surrounding environment, categorize them, and generate some kind of outputs. Similarly, the perceptron is a basic processing element that also receives input, processes it, and generates an output based on the predictive model. More specifically, this predictive linear model, which was developed based on previously labeled datasets, let's place it inside of a node. Our model node is going to receive two input nodes, the age and blood sugar, x1 and x2 respectively. Suppose we want to predict if someone is diabetic. The person is 30 years old, has blood sugar levels of 3 millimoles per liter. As such, the input node x1 is 30 years old, and the input node x2 is 3 millimoles per liter. Assume the line has the following equation. The perceptron will then plot the point on the graph and check where that point is relative to the linear model. Based on this line's equation, if the person's linear combination is positive, they're going to be plotted below the line, and thus output a prediction of 1. Otherwise, if the person's linear combination is negative, they'll be classified above the line, and thus output a prediction of 0. In our case, this person who is 30 years old, with 3 millimoles per liter of blood sugar, has a positive linear combination, is therefore going to be plotted somewhere below the line, along with the other blue points in region 1, and thus we can safely predict that this person is in class 1, they are not diabetic. Let's reshape our perceptron model and consider the bias as an input as well. Meaning, we'll consider the person's age, the blood sugar, and a bias value of 1. Why 1? Well, if you really think about it, what the first node in the perceptron does is it takes the inputs and multiplies each of them by their respective weights. The age x1 is multiplied by w1, negative 0.1. The blood sugar x2 is multiplied by w2, which would simply be 1. And the bias 1 is simply multiplied by the bias value 14, and then taking the sum to obtain the score. There's actually a second node in the perceptron which we haven't talked about, but we've been subconsciously using it all along, and that is the activation function. In neural networks, the activation function of a node is what defines the outputs. The most common type of activation function that we've been subconsciously using all along is the step function. We've established that what the first node does is it takes the linear combination of all these inputs, and now it's the step function which checks the result of our linear combination. If it's positive, the point is below the line and therefore assigned a label of 1. Otherwise, if the score is less than 0, the point is above the line and assigned a label of 0. To recap all of this, our input nodes, whose linear combination is computed, and the model node, whose result is then processed into the activation function, which then predicts the output. All of this makes up our perceptron. Now that we know the basic node composition of a perceptron, Let's further expand into perceptron theory before diving into any code. This line is found based on previous data sets that have already been labeled as either healthy or sick. This sets up a predictive model that can help us predict the labels of new, unobserved data. In our case, we developed a model that predicts the person's likeliness of being diabetic. And from that model, depending on that person's age and blood sugar, if the coordinate lies above the line, then they're likely diabetic, otherwise not. Let us now approach this a little bit more analytically to make a prediction. First, two inputs are processed. The first one is age, which will be denoted as x1, and the second one is the blood sugar, which will be denoted as x2. Accordingly, the horizontal axis corresponds to the variable x1, and you're probably used to the vertical axis being labeled as y. We're going to label it x2, so as to stay consistent and properly denote the second input variable. Right now you and I can eyeball this data and draw a boundary line that separates the two regions considerably well. Eventually we'll implement an algorithm that's able to find this line on its own with minimal error. But let's assume that through hundreds of iterations, our learning system determined that this line best separates our data into discrete classes. We can now use this data to classify new data as either healthy or sick, depending on whether or not the data point falls below the line or above it. This line's equation can be represented as x2 is equal to negative 0.05x1 plus 12. You're probably used to representing the equation of a line as y is equal to mx plus b. Well, this is the same exact thing as y is equal to mx plus b. That is, where y would equal 0.05x plus 12, but it's important that we follow this notation instead so as to properly reference our input variables. What we'll do now is actually rearrange this linear equation by bringing x2 over to the other side, where 0 would equal 0.05x1 minus x2 plus 12. This is still the equation of our line, just rearranged, and the reason why we did this will be very clear momentarily. Let's take this equation, and if you take any point that's above the line, sub it into the linear equation, where in this case x1 is 80 and x2 is 10. Subbing this into our line's equation, we get a negative number. Similarly, if you take any point that's below the line, where in this case x1 is 20 and x2 is 5, sub it into the equation and notice that you get a positive number. This linear model, which we were able to develop based on previous data sets, its equation can be used to determine the score. If the person's score is positive, such that it's greater than or equal to 0, they likely are not diabetic. Otherwise, if the person's score is negative, they likely are diabetic, thus separating our data into two discrete classes. Let's recall the distinction between the label and the prediction. These datasets, they've already been labeled as either red or blue. They have been given a correct output as having diabetes or not. The goal is to use these labeled datasets to train an algorithm to develop a linear model that can accurately classify this data. Initially, the algorithm starts with a random line with some random equation. Notice that x1 and x2 are multiplied by two constants. These two constants are called the weights, which essentially dictate the slope of the line. And this here is known as the bias, whose value dictates where the line intersects the vertical axis. Different weights and biases will result in different slopes and inclinations of our line, as clearly shown. Generally, the equation for a linear model will be written as w1x1 plus w2x2 plus b. What our algorithm will do is look at the initial data that's already been labeled. It will start with some random line to try and classify our training data, a line like this one. Clearly this linear model is not a good one. It misclassifies a lot of the points. Its classification accuracy is not good, and thus its error is very large. What our algorithm will do is it will keep adjusting the weights and biases of our linear model until it comes up with the optimized line that best classifies our data, the line with minimal error. Our algorithm just made use of labeled datasets to train itself and come up with the perfect linear model. Let's assume this linear model has the following equation. We can now confidently use this model to predict the label of new data points. We do so by first determining the score. Suppose we have a person who's aged 40 years old with a blood sugar of 2. We'll then take the linear combination of these inputs, which results in a score of 8. And now we can make a prediction. The prediction is denoted as y hat, which says that if that person with some age and some blood sugar, if the linear combination of their inputs is greater than or equal to 0, if they're positive, they are classified in region 1. Otherwise, if their linear combination is less than 0, if it's negative, they will be classified in region 0. In our case, the score of a person aged 40 with glucose levels of 2 millimoles per liter has a positive score, and thus they can be categorized in class 1 as not being diabetic, which makes sense in the case of this line's equation, since anything above the line will have a negative score, anything below a positive score. The entire focus of this section will be to train an algorithm to come up with a line whose predictions are accurate with data points that have already been labeled. That is, it must be able to correctly classify all the data points with maximum accuracy. There's one more concept we have to understand before we implement this into code, and that is the concept of perceptrons. We can use it to predict the value of new data which don't have a label based on their score. Let's kick things up a notch and relate all of this to the notion of perceptrons. The perceptron is the most basic form of a neural network that takes inspiration from the brain. The brain is a complex information processing device with incredible pattern recognition abilities. It's able to effortlessly process input from its surrounding environment, categorize them, and generate some kind of outputs. Similarly, the perceptron is a basic processing element that also receives input, processes it, and generates an output based on the predictive model. More specifically, this predictive linear model, which was developed based on previously labeled datasets, let's place it inside of a node. Our model node is going to receive 2 input nodes, the age and blood sugar, x1 and x2 respectively. Suppose we want to predict if someone is diabetic. The person is 30 years old, has blood sugar levels of 3 millimoles per liter. As such, the input node x1 is 30 years old, and the input node x2 is 3 millimoles per liter. Assume the line has the following equation. The perceptron will then plot the point on the graph and check where that point is relative to the linear model. Based on this line's equation, if the person's linear combination is positive, they're going to be plotted below the line, and thus output a prediction of 1. Otherwise, if the person's linear combination is negative, they'll be classified above the line, and thus output a prediction of 0. In our case, this person who is 30 years old, with 3 millimoles per liter of blood sugar, has a positive linear combination, is therefore going to be plotted somewhere below the line, along with the other blue points in region 1, and thus we can safely predict that this person is in class 1, they are not diabetic. Let's reshape our perceptron model and consider the bias as an input as well. Meaning, we'll consider the person's age, the blood sugar, and a bias value of 1. Why 1? Well, if you really think about it, what the first node in the perceptron does is it takes the inputs and multiplies each of them by their respective weights. The age x1 is multiplied by w1, negative 0.1. The blood sugar x2 is multiplied by w2, which would simply be 1. And the bias 1 is simply multiplied by the bias value 14, and then taking the sum to obtain the score. There's actually a second node in the perceptron which we haven't talked about, but we've been subconsciously using it all along, and that is the activation function. In neural networks, the activation function of a node is what defines the outputs. The most common type of activation function that we've been subconsciously using all along is the step function. We've established that what the first node does is it takes the linear combination of all these inputs, and now it's the step function which checks the result of our linear combination. If it's positive, the point is below the line and therefore assigned a label of 1. Otherwise, if the score is less than 0, the point is above the line and assigned a label of 0. To recap all of this, our input nodes, whose linear combination is computed, in the model node, whose result is then processed into the activation function, which then predicts the output. All of this makes up our perceptron. Now that we know the basic node composition of a perceptron, let's further expand into perceptron theory before diving into any code. A processing element which receives input nodes, and based on the equation of the linear model, takes their linear combination in the first node. Another node, the step function, then checks the score and assigns that point a label of either 0 or 1. That is the basic composition of a perceptron. It takes in input data, processes that information in some way, and finally decides how to categorize that data by producing an output. We also mentioned that when taking the linear combination of the inputs, each input is multiplied by its respective weights. Looking at this equation, age x1 is multiplied by weight 1, and sugar level x2 is multiplied by weight 2. Looking at this, it should be clear that blood sugar has more weight than age. Suppose someone is 50 years old and has 3 millimoles per liter of blood sugar. If we take their linear combination, it results in a positive value of 6, which our activation function would process and return a prediction of 1. If I change the age by a factor of 10, make it 60 years old, it barely changes the value. Whereas if I change the sugar level by a factor of 10, it has a dramatic impact on the score. The input with the highest weight is the one that has the larger effect on the score. And clearly, blood sugar has the higher effect. Its value is much more influential and pretty much dictates whether or not someone falls in class 1 or class 0, whereas age doesn't really have as much of an effect. In essence, the equation of our line dictates how much weight an input has over the other. Before diving into any more theory, let's dive into some code and set up the initial stages of our project. To set all of this up, this entire lesson will consist of making use of matplotlib and very simple NumPy. If you feel that you're already comfortable with NumPy and don't want to go through setting up the initial stages of our project, then feel free to download the code in the resources folder and move on to the next video where we discuss more neural networks. Going forward with neural networks, we'll be using Jupyter Lab rather than the Atom text editor, which will prove to be a lot more convenient and very similar to Jupyter Notebooks if you did the Python crash course. So what we'll do first is inside of the terminal, we'll navigate to desktop, cd desktop, and inside of desktop we will open Jupyter Lab, and we'll start a new Python 3 notebook. I will call my file, rename, logistic regression. And before we start, if at any point running the cells isn't working for you, make sure to shut down the current kernel session and then restart a new one. And back to our file, we'll minimize this and start off by first importing NumPy as the alias np, and we'll also import matplotlib.pyplot as plt. We'll run this cell, and this subpackage pyplot will contain many useful functions needed to plot our data. First and foremost, we're going to plot 200 initial points onto matplotlib, 100 points for each class. And for the sake of clarity, we'll start with only 10 points. As such, we will set a variable, number of points is equal to 10. We'll start by displaying the points in the top region. So set our variable, top region, is equal to numpy.array. Since we're displaying many points, obviously these points must be contained inside of an array. Each point is going to have a random x1 value and a random vertical x2 value. yet all the points have to be in the top region. So what we'll do is we'll first specify the x1 values. We will set a variable random x1 values is equal to numpy.random.normal. What normal will do is return an array of random normally distributed values. If we imagine a normal distribution, random points are distributed as a symmetrical bell-shaped graph. Looking at this curve, it starts at the center, the mean, and then spreads out over a wider range of values. Similarly, looking at the end result, and specifically at the top region, the center of our normal distribution for this region starts at 10 horizontally, since it looks like most of the points start within that region, and then it spreads out over a wider region. More specifically, our distribution starts at 10 and spreads out over some standard deviation. So back to our code, the center of our point distribution will be at 10. And the standard deviation, which is simply a measure of how spread out the numbers are, I'll put -2. You can make the standard deviation into whatever you want. You can make it bigger, like 3 or 4, which simply means that your points are going to be more spread out from the center over a wider range of values. I'm just going to leave mine at 2. And finally, the last argument is simply how many points we want in our distribution, which will simply be the number of points declared, 10. We'll go ahead and output the variable random x1 values. And it prints normally distributed numbers with 10 as the center of it. Now this array denotes how the points are distributed horizontally. Each point on the graph requires both an x1 and an x2 coordinate. We already distributed our points horizontally. Now we need a corresponding array that also represents how the points are distributed vertically, along the x2 axis, which ideally would start from the middle, upwards and downwards. Looking at the top region of the end result, the center of our points distribution looks to start at the x2 coordinate 12 and spreads over some standard deviation. So back to our code, we will set a variable random x2 values is equal to numpy.random.normal with center 12, standard deviation of 2, and number of points 10. And now we can simply combine the horizontal and vertical coordinates of our top region into a single array. So we'll just put in the random x1 values and the random x2 values. And now that we have the x1 and x2 coordinates for 10 points, let's go ahead and print them out. The first row of data denotes the horizontal positionings of our points. The second row, the vertical positionings. The way our array is formatted currently is a bit problematic, especially once we get into matrix multiplication to calculate the errors in our linear models. This right here is the horizontal coordinate of a single point, and its corresponding vertical coordinate is on a different row. We need all horizontal and vertical coordinate pairs to be on the same row, such that each row will have 2 elements. What we can do is we can take the transpose. The transpose, as we discussed in the crash course, simply interchanges each row with its corresponding columns. The rows become the columns, and the columns become the rows, ultimately giving us our results. We can do this with either a .t or a .transpose, whichever one you prefer. They both work the same way. We'll go ahead and print this out. Both x1 and x2 coordinates for every point are on the same row. Now let's go ahead and display them with matplotlib. We'll write plt.subplots, which simply allows you to display multiple plots on the same figure, and we'll specify a figure size, fig size, which we're going to set equal to a tuple of floats, which will simply be 4 inches wide and 4 inches high. That's the size of our figure. And plt.subplots actually returns a tuple, which we can unpack into 2 values, fig and ax. And you know what? We're not going to be making use of the figure variable, so we'll just leave this blank. And we'll use our axes variable to display a scatter plot of data with ax.scatter. The first 2 arguments will specify the horizontal and vertical coordinates of our 10 points. For our first argument, the horizontal coordinates we're going to access directly from the top region array. And looking at the array, all the horizontal coordinates are in the first column. So what we need to do is access every single row by first referencing the top region array. And we want to index every single row, which we can do with the colon. And we want every row in column 0, the first column. So we'll specify an index of 0. If you're not familiar with indexing, make sure to refer back to the NumPy crash course. And now for the vertical coordinates, top region. Again, we'll use the colon to index every single row in the array, but we want every row in the second index at index number 1. And now, for the sake of concision, what we'll do is we'll declare our random values right inside of our array. Delete those. And finally, what color will our points be? Well, we'll declare a keyword argument color equal to red. R short for red. Final step is to simply show the plot with plot.show. Run your code. And there you have it, 10 points with the random horizontal and vertical coordinates. Let's make this into 100 points. Much better. Now we need to add the points at the bottom region. We'll do this rather quickly by setting a variable bottom region is equal to a numpy array, numpy.array. What we'll do first is specify the x1 values of all these points with numpy.random.normal. And looking at the end result, specifically at the bottom region, clearly the center, the mean of the normal distribution for this region horizontally starts at the coordinate 5. Since it looks like most of the points start within that region and then spreads out over some standard deviation. So back to our code, the center of our distribution will be at 5. And the standard deviation I'm just going to leave out as 2. And how many points we want in our distribution is simply the number of points. As for the vertical coordinates, it seems that the distribution starts at 6 vertically and then spreads out over some deviation. So back to our code, we will write np.random.normal with a mean of 6, standard deviation of 2, and the number of points is simply the number of points. Ultimately, we now have 100 points in the bottom region, 100 in the top, each one with random x1 and x2 coordinates. We just need to display them on our figure. But once again, let's take the transpose and then use our axes variable, ax.scatter, to display a scatter plot of data. The bottom region has the exact same dimensions as the top region, so let's just go ahead and copy that. And instead of top region, we'll write bottom. And our color will simply be blue, B short for blue. All right, let's run the code. And we get our 2 regions of data. Eventually we'll have our computer find a linear model that best classifies them. But before proceeding to that, let's make sure that whenever we run our code, we want our coordinates to stay the same. We want repeatable results. And thus we must seed our number generator. We can do so with numpy.random.seed0. By writing this line of code, it's just a way to get the same random numbers each time you run a program. That way if there's an error in your model, we can reproduce the error every time. And if you keep running the code over and over, notice that the same set of points will appear every time. Simple enough. This was just pure NumPy and Matplotlib, nothing fancy so far. We have our 2 regions of data. The entire goal of our project will be to use this data to train and develop an algorithm to come up with a line that separates this data into discrete classes with minimal error. We'll start implementing that in the next few videos. Use this data to train and develop an algorithm to come up with a line that best separates data into discrete classes with minimal error. As you know, a line can be represented by an equation where W1 and W2, the weights, dictate the slope of the line. These weights start out as random values, and so we're just going to have a random line, which more often than not is not going to classify our data correctly. Clearly this one does not. But as the neural network learns more about what kind of input data it's dealing with, it will adjust the weights based on any output errors that resulted in categorizing the data with the previous weights, until it comes up with a good model. In essence, through every iteration, the network is being trained to come up with a better linear model. And how does it do it? Specifically, how does it know how to adjust the weights? Instead of looking at 200 points, let's simplify our example to 8 points. The blue points are labeled 1, and the red points are also already labeled, but as 0. Now we need a line that best separates this data into 2 classes. You and I can eyeball this and draw the following line. This line clearly separates all of our data correctly, but the computer can't eyeball it. It has no idea how to start. So what it's going to do is display a random line with some random equation. It's then going to look at this line and identify any errors in categorizing the following data sets. Based on these errors, it's going to eventually adjust the weights of the linear equation to fit the data better. We're essentially training the neural network, but how is it going to do that? Let's go back to our first line. Clearly these 2 points are misclassified. Suppose this is our linear equation. If you take the linear combination of each point, each one would result in a negative score, a value of less than 0. And our step function would then predict each one's value is 0, but this is wrong, since we've initially assigned these points a label of 1, but our linear model predicts their value is 0. The key metric to solving this problem is the error, which tells us if our model is doing well or not, depending on how large or how small the error is. And now, through gradient descent, our network is going to take tiny steps to reduce this error in every iteration. These tiny steps correspond to the learning rate, which needs to be sufficiently small, since when the line is fixing itself, you never want it to move drastically in one direction, especially when you have a lot of points. At every step, the line will move closer to the misclassified points, and it keeps doing so until there are no errors, or until the error is sufficiently small, and by doing so, we eventually obtain the perfect linear model. Suppose the perfect linear model for this set of data was defined by the following equation. We can now conclude that in classifying our data, our linear model clearly gives more weight to x2 rather than x1. The main theme of this lesson being, the algorithm starts with a random line defined by random weights. The neural network, as it calculates the errors, it starts to learn more about the input data. It then readjusts the weights to minimize these errors and thus better classify our data. How does it calculate the error? How do we determine which points have the largest error relative to the current linear model? Well, before getting to that, we need to reshape our view on the perceptron model. Let's actually calculate the error. Well, we're going to need a continuous error function. We'll call it E. Looking at this diagram, clearly there are 2 misclassified points. We know the blue points need to be below the line and the red one above. So what's going to happen is, this error function is going to assign each misclassified point a big penalty. As for the correctly classified points, they're going to receive very small penalties. We'll have it such that the size of the points reflects the size of the penalty assigned to them. The misclassified points have the largest penalties since they are misclassified, and what we'll do is detect these error variations and thus figure out in which direction we need to move the line the most. The total error then results from the sum of these penalties associated with each point. We'll safely assume that the total error is very high. So what we'll do is actually move the line in the direction with the most errors. We keep doing that until all error penalties are sufficiently small, and thus we're minimizing the errors as we adjust the weights of our linear model to better classify the points, and thereby minimizing and decreasing our total error sum. Now, what is this error function? In order to answer this question, let's rethink our perceptron model. In the second node, based on the score of each point, it predicts a value of 0 or 1. Any point with a positive score gets a 1, otherwise a 0. These are discrete predictions, which are derived from our step function. The problem with this being, a step function increases or decreases very abruptly from one constant value to another. There is no in-between. Based on the value of the linear combination, the step function is discrete. It's not continuous, it's discrete in the sense that it only predicts values of either 0 or 1. Instead of representing our predictions as discrete values of 0s and 1s, they need to be continuous probabilities, which is why we cannot use the step function. Because suppose we wanted to predict the likeliness of someone who is, let's say, 62 years old with a blood sugar of 7.5 millimoles per liter. We want to predict the likeliness of this person being diabetic. The value of that person's linear combination based on this model is negative 0.1 times 62 years old minus 7.5 plus 14. All of this equals 0.3. As expected, it's a positive value since our point is below the line in the positive region. Our step function would simply check if that value is bigger or smaller than 0. In this case it is, so it predicts a value of 1. This activation function doesn't actually return the likeliness of someone having diabetes or not. It's either a yes or a no, a very firm value. Well, instead of a step function, to determine the probability of someone being diabetic, our activation function is going to be a sigmoid. There are many types of activation functions, but we'll stick with the sigmoid, which is represented by the following equation. What that's going to do is take the value of our linear combination and sub it into the sigmoid function, which returns a value of 0.57, which means that according to our model, this person who's 62 years old with blood sugar of 7.5 millimoles per liter is 57% likely to be healthy, to not be diabetic. Let's say we test a person who's 20 years old with only 2 millimoles per liter of blood sugar. Their linear combination would result in a value of 10. If we sub this value into our sigmoid, 1 divided by 1 plus e to the negative 10, it results in a value of 99%, which makes perfect sense. The younger someone is, the more they tend to exercise, and generally speaking would carry less weight as opposed to when they're older. And the lower the blood sugar, the more effective insulin is in storing sugar inside the cell, the less diabetic risk. In other words, the further you are from the line in the positive region, the lower your blood sugar, the younger you are, and thus the more likely you are to be healthy. The more you're in the positive region. And obviously the opposite occurs as you go into the negative region. As far as errors go with the sigmoid activation function, let's go back to this data set and assume everyone in blue has already been tested, and we've determined they are not diabetic. They already have a label of 1, and everyone in red has also been tested. We've determined they are diabetic. They are already labeled as 0. This is our training data. Our algorithm will try and classify this data, and it will start with some random line. Looking at this data, we can see that this point is misclassified. If we know that the person isn't diabetic, then his predicted probability of being healthy by the neural network should be higher than 50%. However, according to our linear model, this person is in its negative region, which is an error. By adjusting both the weights and bias of our line, it then makes the correct prediction. Going forward, we'll be using the sigmoid function as the activation function, not the step function. That is, we'll proceed with the notion of what is the probability of someone being healthy or not, instead of it being a discrete yes or no. That is all for the sigmoid function, predicting the probabilities of our points. Going forward, we'll need to use the sigmoid function to eventually implement our gradient descent algorithm. In this video, we'll jump back to our code and implement the sigmoid function to predict the relative probabilities of each point relative to some linear model. If you recall, to determine the probabilities, we need to apply the sigmoid function to the linear combination of every single point. Except right now we can't really do that. We have a small problem. Recall in perceptron theory that along with our x1 and x2 input nodes, we consider the bias as an input as well, such that it always has a value of 1. So back to our code, what we'll do is we will set a variable bias is equal to np.1's number of points. And now for every single point in the top and bottom region, it will have a bias value. Bias and bias. Let us now combine both our top and bottom region into a single array. We'll make use of vstack, a function which we saw in the NumPy crash course. What we'll do is we'll stack this array vertically on top of this one. That is, we will write all points is equal to numpy.vstack. We will stack the top region on top of the bottom region. If we just go ahead and print all the points, we get an error. NumPy is not defined, and it looks like I need to run this first cell, then do it. Clearly, every single point has 2 inputs, x1, x2, as well as a bias value. What we need to do now is display some random line as our model. What we'll do first is we will set a variable line parameters is equal to numpy.matrix. Recall from the crash course that a matrix is simply a 2D array with rows and columns, except that it has certain special operators like matrix multiplication, which we're going to make use of. Now, what are these linear parameters? Simply the weights and bias of the line, W1, W2, and B. We'll write let weight 1 is equal to negative 0.2, weight 2 is going to equal negative 0.35, and the bias will be 3.5. These are just some random values which are going to define the slopes and y-intercept of some random line. And now we will simply declare our linear parameters inside of the matrix. You'll see why in a bit. We have our linear parameters. We still need to specify the coordinates of the line. Horizontally, we want our line to go from wherever the first point on the left is to the last point on the right. Obviously, the furthest point on the left will be in the bottom region. Let's access all the horizontal positionings in our bottom region, which we already did over here. So we'll just copy and paste this right under line parameters. And what we want to do is choose the smallest horizontal value, .min. Why? Well, the smallest horizontal value will correspond to the horizontal coordinate of the point that's furthest on the left. We'll call this variable x1. And now how would you find the corresponding vertical coordinate, x2? Well, we know that w1, actually we'll just put this in comments. We know that w1, x1 plus w2, x2 plus b is equal to 0. If we rearrange this equation and simply isolate for x2, what you'll wind up with is an equation like this. So you know what, we're just going to set x2 equal to precisely that. x2 is equal to negative b. And you know what, instead of calling our bias, we'll just call it b for simplicity to keep things consistent. And there you go. Now this cell is actually getting a bit crowded, so what we'll do is actually move showing the plot on a different cell. Copy that. Put it right here. Okay. Alright, now obviously a line is composed of 2 points, not just one. We need the furthest point on the right, which will be in the top region. Let's access all the horizontal positionings in our top region, as we did previously over here. We'll just copy that. And what we want to do is choose the largest horizontal value, .max. Since the largest horizontal value will correspond to the point that's furthest to the right. And now, instead of making another variable, actually, we'll just set x1 equal to a numpy.array. It's going to contain the first horizontal value we declared, the one furthest on the left, and the second horizontal value, the one that's furthest on the right. This variable now contains both horizontal coordinates of our line, and there's no need to actually change x2, since what it does now is, element-wise, computes the vertical coordinates for each element in x1, which will result in a value of 2 vertical coordinates in an array. We can go ahead and print them, print x1 and x2. Our first point will have a horizontal x1 coordinate of negative 0.54, somewhere here, and its corresponding vertical coordinate is 10.3. Our second point has horizontal coordinate 14.53, which is over here, and a vertical coordinate of 1.6. Ultimately, we're going to have a line that goes like this. So we have the 2 points to form our line. What we'll do now is plot this line by declaring a function. First, we'll create a new cell under the first one. We can simply do so by pressing Alt-Enter. And then we'll write def draw, taking in the horizontal coordinates x1 and the vertical coordinates x2. And inside the function, we'll set a variable line is equal to plt.plot. The first 2 arguments simply take in the horizontal coordinates and the vertical coordinate for the second argument. And from those coordinates, it's going to plot the line. So we'll go back to this cell and call the function draw, passing in a x1 and x2. We'll run the cells from the top to bottom, and there's our line. So this is our linear model. It's not perfect, but we're going to use it to calculate the probability of each point being in its positive region, which is simply the sigmoid of the linear combination of all of our points. How do we take the linear combination of all our points? This is where matrix multiplication comes into play. Before doing so, we need to take the transpose of line parameters, .t. Why? Well, recall from the crash course, Matrix multiplication only works if the number of columns on one matrix is equal to the number of rows on another matrix. Let's put this at 5 points for now and run both our cells. If we print the shape of all points.shape, and print the shape of line parameters, line parameters has 3 rows and 1 column, and all points has 10 rows and 3 columns. It should now make sense to you why we took the transpose of all the points in our array as well as the line parameters, simply to ensure compatibility with rows and columns when we conduct matrix multiplication. That way, if we actually print the values of all points and line parameters, if we were to do matrix multiplication between the two, just like we saw in perceptron theory, for every single point, for every single row, x1 is multiplied by w1, x2 will be multiplied by w2, and 1 will be multiplied by the bias value, and then the entire row is added up to obtain the score of each point. And that's matrix multiplication. We've already covered it in the crash course, it's nothing new. So let's go ahead and multiply all of our points by line parameters by writing linear combination is equal to all points times line parameters. If we output this value, linear combination, we obtain the linear combination of all the points, all of them stored in this array. Notice how 6 of the scores are negative, and if you remember, any point that's in the negative region of a linear model will have a negative score. So we have 6 negative values, and accordingly we have 6 points to the negative region of our line, 4 positive values, 4 points in the positive region of our line. It looks like there's only 1 here, but these are just 2 points that are really close together, and obviously our line is misclassifying this point. Alright, so we have all the linear combinations inside of an array. Now for every linear combination value, to make it into a probability, we need to obtain its sigmoid. So what we'll do is, back into our first cell, we'll declare another function, def sigmoid score, and what that will return is the sigmoid equation, which we established was 1 divided by 1 plus e to the negative x. In this case, numpy.exp to the negative score. And what we'll do now is, back into here, make sure to run the cell first, we will set a variable, probabilities equal to sigmoid of our linear combination values. And now we can simply output probabilities. Looks like I forgot to place a return value here. Output probabilities. And this gives us the probability of each point being in the positive region. Notice that 6 of these points are below 0.5 and 4 of them are above, which makes sense since 4 points are in the positive region, so obviously they're going to have the higher probabilities, and 5 of our points, or 6 of our points, are in the negative region, and thus they will have the lower probabilities. We're simply checking how far above or below the point is from the line. The further it is in the positive region, the higher the probability. The further it is in the negative region, the lower the probability. Alright, now obviously this line is not perfect. It's misclassifying this point. This should be in the positive region of our line. We'll go ahead and put this back to 100 points and delete the output. You and I can eyeball this data and agree that the line which would perfectly separate our data is one that would go through here. But how does the computer specifically determine which model better classifies our data? Well, this is where we shift our discussion over to cross-entropy. The computer specifically determine which linear model better classifies our data. This is where we shift our discussion over to cross-entropy. Let's look at these two diagrams in a probability perspective. The best model is the one that gives the higher probabilities for the points that we know should be in the positive region, and the lowest probabilities to the points that we know should be in the negative. And we've already tested this person. They're labeled blue, and thus they should be in the positive. But according to our linear model, this point here is in the negative region since its probability is under 0.5. And anyone that's red, suppose we've tested all of them and we know they're diabetic. Yet this linear model predicts that this point is 80% in the positive, 80% likely of it being healthy, which is also wrong. Clearly, this model better classifies our data since it assigns the higher probabilities to the points we know should be in the positive and the lowest probability to the points we know should be in the negative. For the computer to determine that this model has a smaller error than this one, let's make use of cross-entropy. What we need to do first is calculate the probability of the points being what they actually are. All of these probabilities correspond to the likeliness of something being blue, of being in the positive. For the red points, we need to determine their probabilities of them being red, not blue. And since probabilities add up to 1, their likeliness of being red, of being in the negative, is simply 1 minus the probability of it being blue. On the left-hand side, one of our red points, according to the linear model, is only 20% likely of being red. Which doesn't make any sense. We know this point is red, we already labeled it as such. But according to the linear model, it predicts that it's unlikely for this point to be red. The second diagram makes a lot more sense. All the red points are more likely to be red, all the blue points are more likely to be blue. They are classified correctly. This diagram we know has a much larger error than the second one, and given how we computed the probabilities, the error can be written as the summation of the natural logarithm of each probability. Let's apply this equation to both our diagrams. We get a negative number for both, which makes sense since the log of a number between 0 and 1 results in a negative value. And we're just adding negatives onto negatives, so what we'll do is reverse the sign by taking the negative of our summation. Looking at the results, it's clear that this model has a much larger error. This summation of logarithms is what we'll refer to as cross-entropy. This is a very important concept. When points are correctly classified, they have small error penalties, whereas when points are incorrectly classified, they have big error penalties. It follows that the linear model that better classifies the points is going to result in a low cross-entropy, and a bad model that incorrectly classifies its points has a large cross-entropy value. This gives us a method of determining a good model from a bad model by simply calculating the model's cross-entropy. Let's make this into an actual formula which we can then use in our code in the next video. The general equation for cross-entropy is the following, where P is the probability of a point being blue, and the variable y corresponds to a label of either 0 or 1. If our point is labeled blue, if we tested this person and they are healthy, it will have a label of 1. If our point is red, y will equal 0. This makes sense with what we've done so far, because think about it. Take this point, for example, that's blue. It has a label of 1 and a probability of 0.95, giving you 1 times ln of 0.95, and now the second term cancels out because 1 minus 1 is 0. And remember, for the red points, before putting them into the cross-entropy equation, we need to determine their probabilities of being red, not blue. And since probabilities add up to 1, the probability of the red point being red is simply 1 minus p of blue, which makes sense for this equation. Let's compute it for this point, the one that's 43% likely of being blue. And now, since the red point would have a label of 0, the first term cancels out, and you're left with 1 times the ln of the probability of it being red. And if we keep doing that for every point, notice we get the same results as before. Except now, this general equation that we derived, we can actually use it into our code. That's our official equation for cross-entropy. And by convention, when computing the error function, we consider the average, not the sum, which is why we divide by the total number of points m in the end. Even if we were to take the average, it's still apparent that the first linear model has a much bigger cross-entropy than the second one, and therefore a much larger error. This sets us up for gradient descent, since now we're able to actually calculate the error with cross-entropy. Subsequently, what gradient descent will do is keep minimizing the error and obtain a linear model. Before moving on to gradient descent, and what we'll do now is take this random line, which we plotted earlier, and calculate the error in its classifications. How well does this line separate our data? We'll start by defining a function right over here, def calculate error, which takes in our line parameters. And now the second argument will pass in all of our points, and the third argument corresponds to the labels. We'll call it y, which I'm going to explain momentarily. And let's call our function down below, calculate error. We'll pass in the line parameters, which we'll just copy and paste. And now the second argument, pass in your points, which I believe is called all points. Indeed it is. And now the third argument is going to denote the labels. Since we're classifying points in two discrete classes, either top or bottom, the points in the top region will give a label of 0, and the points in the bottom region will give them a label of 1. The simple reason being, as we saw earlier, given our linear parameters, any point on top had a negative score, and any point on the bottom a positive score. So, instead of 100 points, let's put this back to 10 for now. And what we'll do is actually print the vertically stacked array. Clearly this array has 20 rows. The first 10 rows correspond to the points in the top region, and the last 10 rows correspond to the points in the bottom. We'll need to make an array of labels with 20 rows. The first 10 rows will be all zeros, so as to denote that we're labeling all points in the top region as 0, and the last 10 rows will be all 1s. So back to our code, we'll set a variable y is equal to numpy.array. First, we'll have our zeros, numpy.zeros, number of points, and then our 1s, numpy.ones, number of points. So we'll have 10 zeros corresponding to every point in the top region, and 10 ones for every point in the bottom, 20 labels in total. If we print this, print y. Instead of it being a single row and 20 columns, we need to reshape it into having 20 rows in one column. This is necessary, that way when we apply the cross-entropy function, the dimensions are compatible when performing matrix multiplication. So we'll write .reshape, and we will reshape it as number of points times 2, such that our array will have 20 rows, and we want them going along a single column. Printing this, much better. This is exactly the result that we need. Recall that this was our cross-entropy equation. Clearly, to write this equation, we first need to determine the probability of every point being positive, which we've already done over here. So we'll just copy and paste it right onto our function, and we'll call this p instead for simplicity. And you can delete what we have here, and we'll simply copy and paste that. This is named points, not all points, and delete that as well. Nothing new so far, we just got the probability of every point being positive. And as the equation suggests, we have to take the logarithm of all probabilities with np.log p and multiply it by the label. What we'll do actually is take the transpose of the first term before multiplying it by y, .transpose times y. By taking the transpose of the log of the sigmoid, this becomes a matrix of a 1 row by 20 columns, and by performing matrix multiplication between the two, we get a 1 by 1 matrix. If you're not sure why, make sure to revisit the matrix multiplication tutorial in the crash course. But notice how the points in the top region have no effect on the final value of our first term. This does exactly what we need it to do. It takes the ln of the probabilities of all the points in the blue region, adds them up, and cancels out anything from the top region. Let's go ahead and put in the second term, 1 minus p. This takes the probability of every point being negative, in this case of a point being red. We'll take the natural logarithm, np.log. Once again, take the transpose, but this time multiply it by 1 minus y, 1 minus the label. This time to cancel out any points from the bottom region. Adding these two up gives us our total cross-entropy. But don't forget, by convention, when computing the error function, we consider the average, not just the sum, which is why we divide by the total number of points m. So we will just wrap this up in brackets and multiply everything by 1 over m. The total number of points is simply the number of rows inside of the points array, which we can obtain by setting m is equal to points.shape, which, as you know, well, this should be brackets, which, as you know, returns a tuple of our array's dimensions. The number of rows is at index 0. And don't forget to take the negative, since logs of probabilities ultimately result in a negative value, and we're done. That is our cross-entropy equation. Let's just set it equal to a cross-entropy variable and simply return our value. Return cross-entropy. In our last cell, make sure to pass in all of the correct arguments, and we will print the return value of this function. We get an error. Tuple object is not callable. Seems that there's a mistake somewhere here, and I forgot to add a multiplication symbol. Let's try this again. And we get an error of 0.3178. Our linear model, how well does it classify our data? Well, it does it with an error of 0.317. What if we tried a line that classifies almost everything completely incorrectly? Let's declare a line. We'll choose a line with a y-intercept of 0, a weight of negative 0.1, and W2 of negative 0.15. Let's run every cell. Clearly this line misclassifies all the blue points. It classifies them all in the negative region. As such, clearly this line has a much bigger error than the previous one, 0.84. This is a very bad model in classifying our data. Alright, that is all for using cross-entropy to determine the total error of a linear model. The next step is to use gradient descent to minimize the error and come up with the perfect line. Data, the computer will display some random model. Based on that model, it needs to calculate the error as we did previously. But now what we'll do is use gradient descent to minimize that error and obtain a better linear model which better classifies the data. And we keep doing that over and over through many iterations until we obtain the perfect line. To minimize the error, what we need to do is first take its gradient, its derivative with respect to the weights. If we were to add the gradient to our linear parameters, weight 1, weight 2, and the bias, what that will do is result in new weights and biases of a line with a much higher error function. Accordingly, by subtracting that value, this tells us the value that's going to decrease the error function the most. Ultimately, this results in a linear model with a smaller error. That new linear model, once again, will calculate its error function, subtract its gradient, and keep doing that over and over, minimizing the error function, eventually obtaining a line with small enough error that correctly classifies our data. Unfortunately, in Python, we're not able to simply take the derivative of the error function, but have to actually derive the equation ourselves and then code it. If you're interested in the math behind how the equation is derived, I've included it in the subsequent article. But to keep things short, the gradient of the error function will simply be obtained by multiplying the coordinates of the points by the prediction minus the original label divided by the number of points. Subtracting this value from our linear parameters results in new updated weights for a new line, which will thereby have a smaller error function than the previous. One more thing we're going to do is, we want to take very small leaps from one line to the other. We don't want the value of our lines to change drastically in each iteration. We know that subtracting the gradient adjusts the weights of the line in the direction which gives us the least error, but we don't want the line to move too far in that direction. So we'll scale our gradient down by multiplying it with what's called a learning rate, which is normally a small value of, let's say, 0.01, something small. This ensures that we're still going in the direction that best minimizes our error, but we're doing it in small steps, and that's the formula for gradient descent. Let's apply it to our code in the next lesson. Plus a linear model that better classifies our data until it comes up with the perfect line. Thinking in terms of a perceptron, this linear model with some equation can now receive new unlabeled inputs and output the probability of the point being in the positive region. This is known as feed-forward, the process neural networks use to turn input into an output. And this perceptron is the most basic form of a neural network. Really, all of this ties back into the concept of supervised learning, since in our code we started with a data set, where each point in our data is defined by a label. Every point in the top region was labeled 0, every point in the bottom was labeled 1, and we used this labeled data to train our network to come up with the best linear model that classifies them. That way, when we receive newly input data that are unlabeled, using our model, we're able to make a prediction that properly classifies it, obtaining an output. This is the simplest type of feed-forward. But to end our discussion on perceptrons, let's talk briefly about backpropagation. This is a term you're going to hear quite often in this course, even though we've already implemented it in our code. When training our neural network, initially it starts with a random line, which more often than not will misclassify all of our training data. Backpropagation is something which was implemented when we wrote the code for gradient descent. When there are misclassified points, the error function will result in a large value, and so it keeps updating the weights as well as the bias value to then obtain a linear model that best classifies the data. That is really it for backpropagation. We'll see more complex implementations of it once we deal with multi-layered neural networks, but for now, this concludes our discussion on the most basic form of a neural network, the single perceptron. Perceptron with pure Pythonic code. Its implementation was a little bit too complex and a bit tedious. But now we have a deep understanding of how training occurs under the hood. At the same time, what if there was an easier way to implement this perceptron-based network? Let's have a look at that in the next section. Be surprised at how easy KRS makes it to train fully functional deep neural networks. For the purposes of introducing you to this library, in this section we will only use it to build a simple perceptron-based network. Let's dive right in. Surprised at how easy KRS makes it to train fully functional deep neural networks. For the purposes of introducing you to this library, in this section we will only use it to build a simple perceptron-based network. Let's dive right in. Welcome back. Now that we've finished the installation, let's jump into some code. First and foremost, we'll open up a new Jupyter notebook. Inside of your terminal, we will navigate to Desktop, CD Desktop, and we will open up a new Jupyter Lab instance. Alright, we'll start a Python 3 notebook, which we will rename as perceptron.ipynb. You can go ahead and call it whatever you want. Just like before, first we need to plot our training data just like we did in the last section. Since I've already explained this, we're not going to reinvent the wheel. So first we will just import numpy as np, and we'll also import matplotlib.pyplot as plt. Pretty standard stuff so far. We'll just run this cell, and what I actually did is prior to this lesson I've left you an article with a piece of code that I want you to use inside of your project. So make sure to do just that, copy and paste it and run your code. Again, we've already covered this. If you're not sure what this code does, make sure to revisit in lesson number 7 of the last section. But essentially, we're just declaring 500 points in the top region, 500 points in the bottom region, such that they're normally distributed with a standard deviation of 2. We're then stacking these points in an array and plotting them onto matplotlib. And right here is just the array of labels, which corresponds to all points in the top region having a label of 0, all points in the bottom region having a label of 1. And lastly, we want repeatable results every time we run our data, which is indeed what we have thanks to np.random.seed, which simply seeds our number generator. That way, if we ever have an error in our model, we can reproduce the error every time. Now again, all of this stuff should be very familiar to you. If not, make sure to revisit the last section. And before we get started, to render the figures in our notebook as static PNGs, we will write the command %matplotlib inline, nothing major. Anyways, to get started with the good stuff, what we'll do first is we will import the keras library, and from the keras.model subpackage, we'll need to import the sequential class. A sequential model, as per the official documentation, is a linear stack of layers. Neural networks are actually organized in layers containing interconnected nodes. In the most basic case of a neural network that we previously discussed, the perceptron, the first layer was actually the input layer, which was processed via a linear system of weights and biases, and the output layer resulted in a predicted output via the activation function node. So in this perceptron we have two layers, the input layer and the output layer, nothing else. So what we'll do is inside of a new cell, we will set a variable model equal to an instance of sequential. Having defined the sequential model, let's first run the cell. Alright, having defined the sequential model, we can now start adding layers to the structure. As mentioned earlier, we are going to create a perceptron with an input layer containing two nodes and an output layer with a single node. Using the model.add function, we can now begin to add layers to our neural network. What we'll do first actually is from the keras.layer subpackage, we'll need to import the dense class. In a dense layer, every node in the layer is connected to every node in the preceding layer. So inside the argument, we will specify the properties of the dense layer. The first argument is the units, which will simply equal 1. We'll have a single output for our perceptron, and since this is the first layer being created, we must also define a number of input nodes. This is done through the second argument, input shape, which we will set equal to 2. Since recall in the old code, we only had two input nodes, x1 and x2. Perfect. The final argument, the activation, defines the activation function used in the output layer nodes of the perceptron. Really all we've talked about so far is the sigmoid function, and that's what we used in our old code. So we'll just go ahead and write that. And if you were to actually compare this to how we implemented sigmoid in pure Pythonic code, this is clearly much more concise. Instead of specifying the math yourself, all you have to do is write the tag sigmoid. Alright, having specified the layers of our network, to compile a keras model, we need to make use of an optimizer. So what we'll do is from the keras.optimizers subpackage, we will import Atom. The Atom optimizer is one of many optimization algorithms. What's distinctive about the Atom optimizer is its adaptive learning method algorithms. To truly understand the importance of the Atom optimizer, let's talk about the vanilla gradient descent algorithm that we implemented in the last section with the following formula. By taking the current parameters and subtracting the partial derivative of the error function with respect to its parameters, we're iteratively taking a step in the direction of the negative of the gradients, in the direction of the least error, and therefore updating the weights and the bias in the direction with the least error. The problem with taking this derivative is it's too expensive, since we're essentially just multiplying a scalar times the coordinates of all the points. What if we're dealing with 1,000,000 points or 100,000,000 points, which represents the population of some country? The fact that we're looking at all the training examples at the same time is why we refer to this form of gradient descent as batch gradient descent. In order to compute this derivative term, we have to read into our computer's memory all 100,000,000 records, then taking the derivative and multiplying the learning rate, and we're doing all of that just to take a single step in the direction that minimizes the error. Then to take another step, we have to repeat this entire process, which would be very computationally intensive. and would take a very long time for the algorithm to converge to an absolute minimum. A more efficient algorithm that better scales to large datasets is stochastic gradient descent, which would be much more computationally efficient than the vanilla gradient descent. Why? Well, as we just saw, batch gradient descent computes the gradient using the entire dataset, whereas stochastic gradient descent computes it through a single sample. If you're interested about the specifics of stochastic gradient descent and how it works, feel free to ask me in the Q&A or just send me an email, we can discuss it further. But for the sake of moving on to the code, the atom optimization algorithm is a combination of two other extensions of stochastic gradient descent, notably AdaGrad and RMS-prop, and is a very efficient stochastic optimization method in updating the weights of our network. What distinguishes it is that in stochastic gradient descent, or even the vanilla gradient descent algorithm that we implemented in the last section, is we had to be careful to choose a proper learning rate. A learning rate that is too small leads to very slow convergence towards the minimum, while a learning rate that is too large can hinder the convergence. Where these variants maintain a single learning rate for all weight updates, such that the learning rate does not change during training, the atom optimization algorithm ultimately it computes adaptive learning rates for each parameter, and has been empirically shown to be a very popular algorithm in efficiently achieving good results when dealing with large models and datasets. In practice, Atom is actually currently recommended as the default algorithm to be used, so we'll go ahead and use it ourselves. So what we'll do is we will set Atom is equal to an instance of Atom, which will minimize the error with a learning rate, LR, is equal to 0.1. Now, before training our model to classify this data, we need to configure the learning process, which is done via the compile method, model.compile. Inside of compile, we need to specify what kind of optimizer we're going to use, what kind of error function, hint hint, cross entropy, and the metrics, which is a function that's used to judge the performance of our model. So the optimizer we'll use is Atom. Our loss function will equal some form of cross entropy, which, as you know, is the loss function that will help determine the error. Now, since we're only dealing with two classes, we'd expect a binary outcome of zeros and ones. And thus, we will be using binary cross entropy. Binary cross entropy. This calculates the cross entropy value for binary classification problems. If we were dealing with 3 or more classes, you would then use categorical cross entropy, which calculates the cross entropy value for multi-class classification. As for the metrics, a metric is very similar to a loss function. However, unlike the error function, whose results, as we saw, are constantly backpropagated to minimize the error of our model, the results from evaluating a metric are not used to train the model, but simply to judge the performance at every epoch, which is going to equal a list of functions. In our case, we're interested in the accuracy, which calculates the accuracy of how often the model's predictions match the labels of our data. Now, to actually train a model to fit our data, we'll use the model.fit function. This is the function that we use to start training our perceptron. To start training a model that perfectly classifies our data, we will first pass in the training data that we're going to use to train our model. X is equal to X, that's the keyword argument you have to specify, and then we will pass in the labels that we assigned to each data points. Y is equal to Y, such that labels of 0 will correspond to the top region and labels of 1 will correspond to the bottom region. Alright. And this makes sense, since by passing in the corresponding labels that we assign to each data point, that way it can distinguish as to which point should belong to which class. If, according to the labels, our points are misclassified, the error function will be high, and thus, through an optimization algorithm, we will act to minimize that error, so really important that we pass in the labels. So now we have our training data defined by their labels, And we'll be training our model to fit all of this data. Since all the data is labeled, that way the model can distinguish which points would belong to which class, and then we'll set the verbosity, verbose, is equal to 1. What that will do is simply display a progress bar of information relating to the performance of our model at each epoch. If you set verbosity equal to 0, it simply wouldn't print anything and we wouldn't know what's going on. And now an epoch, you might have noticed me talk about it a lot but never actually explain it. An epoch simply refers to whenever it iterates over the entire data set of points and labels to try and separate our data in discrete classes based on their assigned labels. So every time it iterates over the entire data set of points, that is an epoch. However, one epoch is too big to feed to the computer all at once, so we need to divide it into several smaller batches. More specifically, it will be a batch size of 50. You want to make sure your batch size is sufficiently big, that way it doesn't take forever to run your code, but you don't want it to be too big, since you don't want to feed it to your computer all at once. And since we have 1000 data points, 500 here and 500 there, with a batch size of 50, it will take 20 iterations to complete one epoch. And at each iteration, it's going to update the weights of the neural network, minimizing its error, that way it better fits the data given. And ultimately, the batch size really depends on the size of your data, and according to your GPU, how long it takes to process your data. A batch size of 50 is a pretty good number relative to the amount of data points that we have. Alright, now how many epochs should our line go through? Let's recall the concept of gradient descent, which updates the weights and biases of our network in the direction that decreases the error function the most. It's an iterative process, which is why we need to pass the full dataset through our neural network multiple times to ensure an optimized result. In other words, we need more than one epoch. If you simply specify one epoch, epochs is equal to 1, that leads to the underfitting, which doesn't capture the underlying trend of data. As the number of epochs increase, the more times it's able to update the weights of our neural network, minimizing the error and thus producing the optimal results. At the same time, you don't want to pass in too many epochs, since that can lead to overfitting, which is a modeling error that occurs when a function is too closely fit to a limited set of data points. This overfitting, we're going to see a lot of examples of it once we deal with deeper neural networks. And now, since we're dealing with a linear classification of relatively small complexity, as opposed to a deeper neural network with a higher complexity, which we will make use of later on in the course, one might think that overfitting isn't much of an issue, although a linear classifier can absolutely be overfit if used without proper care. However, if you have the right number of epochs, it's going to model your data just fine. Unfortunately, there isn't really a right answer as to how many epochs you should have. It really just depends on your data set. So what we'll do is we'll just specify epochs is equal to 500. It'll go through all of our data 500 times. Now 500 epochs is a bit much, I'll admit. Realistically, we're not going to need more than 10 epochs or so, but for the sake of demonstrating the training process and seeing a descriptive plot, we'll extend the training process to go with 500 epochs. Now don't actually get used to specifying too many epochs. You'll see that this can get pretty bad once I demonstrate this in the convolutional neural network section, as the model can start to overfit our training data and isn't able to generalize itself to new data. But regardless, we'll cross that bridge when we get there. Now finally, we're gonna set shuffle is equal to true. This one should be new to you. So as to shuffle our training data before each epoch. As we use gradient descent to update the weights in the direction that decreases the error the most, as it keeps minimizing the error, it'll tend to get stuck in a local minimum of some sort, rather than the absolute minimum. And our goal is to minimize the error the most, so what you want to do is ensure the absolute minimum of your loss function, to decrease the error as much as possible, thereby maximizing the accuracy of our model. And so if you are dealing with static training data that's unchanged over all training iterations, gradient descent algorithms will tend to get stuck in these local minima, and the solution to this is to simply shuffle your training data. So what that does is it shuffles the rows in your data, and for each given iteration, trains only a subset of them. This ensures that the subset of training data changes with every single iteration. And thus, if our algorithm were to get stuck, it would simply help it kind of bounce off the local minimum. Alright, we are finally ready to run our code. And you know what, before doing so, and I'm noticing an error, this should be a lowercase y. We don't have any variable that's a capital Y. And aside from that, we should be good to go to run our code. It says the name dense is not defined. Maybe we need to run our first cell. Let's try that. Alternatively, you could have just pressed run all, but we'll just stick with that for now. And look here. What it's doing is training the model in a given number of epochs. Notice that at every epoch, the loss function actually decreases, and its classification accuracy as to how well the model's predictions actually match the labels we gave our training data increases in each subsequent epoch, to a point that it starts to exceed 95% accuracy, which is pretty good. So we've successfully trained a neural network to learn how to classify this data in just a few lines of code. Think of how easy and concise that was doing it with Keras, compared to how long it was in pure Pythonic code, and how many lines of code it took. Although having done all of this in pure Pythonic code, now you should have a better sense of what goes on under the hood when you specify functions like sigmoid, cross-entropy, and so on. And so what this function also does is it returns a history object. It keeps a record of the training loss and accuracy values at every single epoch, which we can get a visual of in matplotlib. So what we'll do is actually set a variable h for history is equal to the return value of our fit function. We'll rerun that. And inside of this cell, I'll just wait for the epochs to finish and fast forward this video. Alright, and with the pyplot subpackage plt, we will make a plot of the accuracy values which we can access from h.history. And from this history attribute, we can access all the values of our accuracy from the key ACC for accuracy. We will give our plot a title, plot.title of accuracy. We'll also label the horizontal x-axis, plt.xLabel. We will label that one epoch. And we will give the plot a legend, which takes in a list, but we only have one curve in our plot. Well, we're only going to have one curve in our plot, which we will call accuracy. Let's run our cell. Alright, and notice how at around 10 epochs, our model pretty much reaches maximum accuracy, so realistically we didn't really have to do 500 epochs. Again, it really depends on the type of training data that you're working with. Alright, now inside of a new cell, let's actually just copy and paste this code. And instead of plotting the accuracy, we'll plot the loss. We will rename our title and legend as well to loss. Run our cell. And looking at this, it's clear that the loss, the error, is completely minimized once we get to about 10 epochs. And then it just kind of saturates from there. So clearly our network model, after numerous epochs, came up with a really good model in classifying our data with minimal error and maximal accuracy, all in a few lines of code. 5 lines of code to be specific. Now it's time to actually display our. Mastering deep neural networks will eventually transition to us learning all about convolutional neural networks, which we're then going to use to extract specific features from images. In our case, we'll be using it to extract image features from traffic signs, thereby helping us classify them, and also extract image features from a specific part of a track in the self-driving car simulation to help predict the appropriate steering angle. But before getting to any of that, we must grasp the concept of deep neural networks. We'll take care of. How are we able to obtain this curve? Well, what we're going to do is combine 2 perceptrons into a third one. To better illustrate this, we'll superimpose 2 linear models to form a single nonlinear model. Obviously, this linear model incorrectly classifies our data. This model also incorrectly classifies our data, although combining them gives us a correct model. This model is actually a linear combination of the two other models. Let's treat each linear model as an input node, which contains some linear equation. Let's refer to this first model as x1, and the second model as x2. What we're doing is multiplying each linear model by some weight. x1 is multiplied by some weight, weight 1, and x2 is multiplied by weight 2. And recall that we also consider the bias as a node as well, which is multiplied by some bias value. Everything is then added up to obtain the linear combination. And recall that subsequent to the linear combination, we apply the sigmoid activation function, ultimately resulting in the following curve. Let's assume W1 is 1.5, W2 is 1, and the bias value is 0.5. Suppose in the first model it predicts that for this point, its probability of it being in the positive region is 0.88. I made the point a little bigger than the others just so you're able to see it, but it's a point in our model just like any other point. And in the second model, it assigns that same point some probability of 0.64. When we're superimposing both linear models, we're adding them together. We're taking their linear combination. Thus, we're also taking the linear combination of the probabilities of every single point. In the case of this point, which in this model has a probability of 0.88, and in this model, which has a probability of 0.64, we multiply the point in the first model with weight 1, and the point in the second model with weight 2. Multiply 1 with the bias value, adding them up to obtain the score. And since we're taking the sigmoid of the linear combination of both of our models, we're also taking the sigmoid of all the linear combinations of our points, which converts them into probabilities. In our case, the sigmoid of this particular point is 0.92, which in our new model, that exact same point is 92% in the positive. Now to obtain this model, before adding the two models up, we're multiplying each one by its respective weights. And recall that the input with the highest weight is the one that has the larger effect on the result, and pretty much dictates what the resulting model looks like. In this case, the first model has a higher weight than the second one, but not by much. Although it's fair to say that the resulting model looks a little more like the first one than the second. Say for example we wanted the second model to have more weight than the first model. That is, instead of a weight of 1, we'll give x2 a weight of 3. That way, when we take their linear combination with the new weights and apply the sigmoid, the resulting model is going to look a lot more like the second model. Clearly, it has a much larger effect on the final result. Accordingly, since we're taking the sigmoid of the linear combination of both our models, we're also taking the sigmoid of all of the linear combinations of all of our points with our new weights. In the case of the point, which we plotted previously, recall in the first model it had a probability of 0.88 and 0.64 in the second. We're multiplying the point in the first model with a weight of 1.5, and that same point's probability in the second model with a weight of 3. Also taking into account the bias. Adding them all up to obtain the score, taking the sigmoid, and this results in a probability of 0.97. Now obviously, this isn't a very good model. It misclassifies many of our points. So let's revert it back to our first model having more weight than the second one. That way, it has more of an effect on the final result. The point being, linearly combining existing models to create new models that better classify our data is the core of complex neural networks. Even though it's your first time doing it, this should be very familiar to you. This looks a lot like what we dealt with in perceptron theory, to come up with a new model that better classifies the data. First and foremost, this linear model, whose line is represented with the following equation, negative 4x1 minus x2 plus 12, we can represent it with this perceptron. The weights in the input layer, negative 4, negative 1, and 12, represent the equation of the linear model to which inputs are being passed in to obtain their probability of being in the positive region by multiplying each input with its respective weight, along with the bias value to obtain their linear combination, and then taking their sigmoid. This is nothing new. We've already seen this stuff in perceptron theory. Our second model with the following equation, negative 1/5 x1 minus x2 plus 3, receives the exact same input nodes, which are processed by our linear model by multiplying each input with its respective weights, and adding it up along with the bias to obtain their linear combination, and then taking the sigmoid of the point to obtain the probability. And recall that we combine these two perceptrons, we combine the two linear models to obtain this one, by multiplying the two models with some set of weights and added it to some bias to obtain a new model. In our case, we assigned the first model 1.5 times the weight of the second one, then took its combination along with a bias of 0.5 and applied the sigmoid to obtain the following curve. So it's important to note that in the input layer, the weights indicate the equation of the linear model, and these weights are used to obtain an output, a prediction of the probability of the points being passed in. And in this layer, the weights dictate how the two linear models are combined to form this nonlinear model. To represent this, we'll add another perceptron by first taking the linear combination of our current ones. Don't forget we always consider a bias of 1, where the first linear model, the first perceptron, is multiplied by a weight 1.5, and the second perceptron is multiplied by a weight of 1, taking their combination along with a bias of 0.5, and then applying the sigmoid to obtain the curve. All we're doing is taking the combination of our models and applying the sigmoid to then obtain a nonlinear model which better classifies our data. Going back to our previous example, suppose we had two inputs, x1 and x2, which represent a single point at coordinates 2 and 2. And we wanted to obtain the probability of the point being in the positive region in the nonlinear model, the model which best classifies our data. These two inputs, the point at coordinates 2 and 2, is passed into the first layer, which consists of two linear models. The two inputs are processed in the first linear model to obtain the probability of the point being in the positive region by taking the inputs as linear combination based on the weights and bias of the model, and then taking the sigmoid. We obtain a probability of 0.88. It is therefore 88% likely that the point is in the positive region of this model. We also obtain the probability of the point being in the positive region of the second linear model, which ultimately results in a value of 0.64. In the first model, this point is assigned a probability of 0.88, and in the second one, a probability of 0.64. When we're superimposing both models, we're adding them together. We're taking their linear combination with respect to weights of 1.5, 1, and a bias of 0.5. Thus, we must do the same thing for our point in the first and second model. We multiply the point in the first model with the first weight 1.5, and the point in the second model with the second weight of 1, adding everything up along with the bias to obtain the score. And since we're taking the sigmoid of the linear combination of both our models to obtain a new model, we must do the same thing for our points, which ultimately converts it to a 0.92 probability of it being in the positive region in the nonlinear model. What you just saw is known as the feed-forward process of a deep neural network. If you're confused by it, we'll cover it in a lot more depth later on. For concision, we can rearrange the notation of this neural network. Instead of representing our point as two distinct x1 and x2 input nodes, where each one goes into a separate model, we can represent it as a single pair of x1 and x2 input nodes. That is, instead of having two of the same x1s, we'll have a single x1 that's multiplied by the weight of the first linear model and multiplied by the weight of the second linear model. We'll also have a single x2 that's multiplied by the weight of the first model and the weight of the second, and the same goes for the bias. It's multiplied by the bias value of the first model and the bias value of the second, and this is really the exact same thing as what we had previously. Nothing changed, since the same concept applies, as we're still taking the linear combination and sigmoid of our point in the first model to obtain a probability of 0.88. We're still taking the linear combination and sigmoid of our point in the second model to obtain a probability of 0.64, and doing it again with respect to weights of 1.5, 1, and 0.5 to ultimately obtain the probability of the point being in the positive region in our optimized nonlinear model in the final layer. This demonstrates the unique architecture of a neural network. The first layer is called the input layer, which contains the inputs x1 and x2, But now, unlike our single perceptron-based model that we saw in the last section, instead of processing these inputs directly in the output layer, first they must go through the hidden layer, which is simply a set of linear models, and the final layer is the output layer, which resulted from the combination of our two linear models to obtain a nonlinear model. The more hidden layers we have, the deeper our neural network gets. Hence the term deep neural network. We're simply using the models in the hidden layers to combine them and create nonlinear models which best classify our data. Sometimes our data is so complex that we'll have to even combine nonlinear models to create even more nonlinear models. We can do this many times with even more hidden layers and obtain highly complex models, like the one you're seeing right now. Data this complex requires many hidden layers of models combining into one another with some set of weights to eventually obtain a model that perfectly classifies this data. From that model, we can then produce some kind of output through a feed-forward operation, although the inputs would have to go through the entire depth of the neural network before an output is produced. If you really think about it, really all of this is just a multi-layered perceptron. If we go back to the perceptron from our diabetes example, we used gradient descent to eventually obtain the perfect linear model to predict whether someone was likely to be diabetic or not. However, in order to obtain this model, there were no hidden layers, simply one input layer and one output layer. The reason why we don't need any hidden layers is because this data's trend is very straightforward. A linear model is enough to perfectly classify it. The same concept applies here with deep neural networks, except in deep neural networks, our data's trend is not straightforward. As you can see here, it's very complex. And so this nonlinear boundary is just an accurate model that correctly classifies a very complex set of data. However, to obtain this nonlinear boundary, we need many hidden layers, each layer containing models that combine into one another to produce this very complex boundary that classifies our data. The more layers you have, the deeper the neural network, and deeper neural networks can be trained to learn even more complex functions, to classify even more complex data. To conclude this lesson, let's have a more general representation of our neural network, such that x1 is multiplied by w11, so as to indicate the first weight in the first linear model, and it's also multiplied by w12, indicating the first weight in the second linear model. And accordingly, x2 is multiplied by w21, the second weight of the first model, and w22, the second weight and the second model. And the bias is denoted as 3, it's multiplied by w31, the bias value in the first model, and w32, the bias value in the second model. For every weight and bias value, we'll add a superscript 1, so as to indicate the first input layer. We'll do the exact same thing for the hidden layer, except now the superscript is 2, since this is the second layer, which eventually leads to the output layer. That is really it for the architecture of deep neural networks. All we're doing is simply combining models to obtain more complex nonlinear models that best classify complex data. To obtain nonlinear models which best classify our data, we also saw how the combination of lines with different weights and biases can result in different nonlinear models, some better than others depending on which input we assign more weight to. Now, how does the neural network know what weights and bias values to have in each layer? That way, the combination of our hidden layers can result in the most accurate model. Well, it's really no different than how we did it for the signal-based perceptron model. We're still making use of a gradient descent optimization algorithm which acts to minimize the error of our model by iteratively moving in the direction with the steepest descent, the direction which updates the parameters of our models while ensuring the minimal error. It updates the weights of every model in every single layer in order to obtain this final model. We'll talk more about optimization algorithms and backpropagation of deep neural networks in the next lesson. But for now, it's important to recognize that subsequent to the training of our neural network by dividing our data samples through some decision boundary, the process of then receiving an input to produce some kind of output to make some kind of prediction is known as feed-forward. Feed-forward neural networks are the core of many important neural networks, such as convolutional neural networks, which we're going to cover very extensively in this course. But we've already seen examples of feed-forward neural networks. It simply means there aren't any feedback loops or connections in the network, simply an input layer, a hidden layer, and an output layer. Although do note that there can be multiple hidden layers, which simply depends on what kind of data you're dealing with. The number of hidden layers is known as the depth of the neural network. Deeper neural networks can learn more complex functions. The input layer first provides the neural network with data, and the output layer then makes predictions on that data based on a series of functions, activation functions. The most widely used activation function is actually the ReLU function, which we will cover later on. To gain a solid grasp on the feed-forward process, let's approach this mathematically. First, the inputs are fed to the network. We'll represent that as a matrix x1, x2, and 1, where 1 is the bias value. We saw that each input is multiplied by weights with respect to the first and second model to obtain their probability of being in the positive region in each model. This might seem a bit intimidating once we represent this mathematically, but I promise it'll make much more sense once we go through an example. So, to represent this mathematically, what we'll do is we'll multiply our inputs x1, x2, and b by a matrix of weights. We'll be performing matrix multiplication, which I'll demonstrate momentarily. But notice how the matrix is denoted as superscript 1, so as to denote the first layer. Ultimately, what that will do is give us the score of the point that's represented by these inputs in each model, and then as you know, by taking the sigmoid of our scores, it gives us the probability of the point being in the positive region in both models. Subsequently, the probabilities we obtained, we now have to multiply by the second set of weights. Notice how we always include a bias of 1 whenever taking a combination of inputs. This set of weights, if you recall, is responsible for the combination of the linear models in the hidden layer to form the nonlinear model in the output layer. As such, the inputs x1 and x2 which exist in our models are also multiplied by these weights and then eventually added up to obtain the score in this model. And as you know, to obtain the probability of the point being in the positive region of this model, we take the sigmoid, and thus producing our final output in a feed-forward process. All of these equations might seem a little intimidating, but it's really easy if we look at an example. Recall the neural network that we had previously, with the following linear models in the hidden layer, which combine to form the nonlinear model in the output layer. Obviously, the nonlinear model is what best classifies our data. So what we want to do is use our nonlinear model to produce an output that describes the probability of the point being in the positive region. To do so, we'll use this representation of the multi-layered perceptron to carry out the operation. The point was represented by the coordinates 2 and 2, so that, along with a bias of 1, will represent the inputs. The first linear model in the hidden layer, recall, was defined by the equation -4x1 minus x2 plus 12, which means in the first layer, to obtain the linear combination, the score of the point in our first model, the weights that the two inputs are multiplied by are -4 and -1, and the bias value is multiplied by 12. To obtain the linear combination of that same point in our second model, the weights that the two inputs are multiplied by are -1/5, -1, and the bias value is multiplied by 3. By performing matrix multiplication, which I've already shown you how to do in the NumPy crash course, you end up with the linear combination value. The score of the two inputs in each model in a 1/2 matrix. The score of the point in the first model is 2, the score of the point in the second model is 0.6, and now, according to the equation we previously derived, to obtain the probability of the point being in the positive region relative to both models, we simply apply the sigmoid to both points, which recall is 1 divided by 1 plus e to the -x. This gives us a probability of 88% of it being positive in the first model and 64% of it being positive in the second model. Now we're at the second layer, and the second layer, recall, contains the weights which dictate the combination of the linear models in the first layer to obtain the nonlinear model in the second layer. In our case, our algorithm determined weights of 1.5, 1, and a bias value of 0.5. So now, continuing with our equation, we have to multiply our probabilities from the first layer with the second set of weights, and don't forget to include the bias value which we have in each layer. Multiplying this to the set of weights 1.5, 1, and 0.5, this results in a final score of 2.46. Taking the sigmoid of this gives a probability of 0.92, and that right there is the math behind the feed-forward process, where the inputs from the input layer traverse the entire depth of the neural network, and based on a series of sigmoid functions and linear combinations that it goes through from one layer to the next, eventually it reaches the output layer, which makes a final prediction and produces the final output. In this example, it only had to go through one hidden layer, eventually producing an output of 0.92. Whether you have one hidden layer or 20 hidden layers, the computational process is the same. Now let's imagine that we had a really bad model, which places most of our red points in the positive region, even though we know they should be in the negative, since they've been labeled as such. Obviously, this model has a very high error. We need to train our algorithm to come up with a better one, network, to eventually produce some kind of output. We then saw an example of a model which incorrectly classifies our data, which is why we're going to shift our discussion over to backpropagation. We need some kind of algorithm to train our model to better classify this training data, and really, it's no different than how we previously did it for the single perceptron. We've already labeled this training data as either 0 or 1. Everything red denoting a label of 0, and everything blue a label of 1. What we can do now is take our training points with random x1 and x2 coordinates and pass them all into our neural network in a feed-forward process, which ultimately is going to produce an output. As you can see, some of the predictions made by the model are correct, but a lot of the predictions on the red points are incorrect, which makes sense since the model clearly misclassifies a lot of them. Since we've already labeled all of this data, the output predicted by the neural network is compared to the actual output which we've already labeled. We're comparing the difference between the two to obtain some kind of error. The more our model misclassifies the points, the larger the error. And just like how we implemented gradient descent on a single perceptron, this error is then backpropagated to constantly update the weights of our neural network, thereby updating all the models and gradually decreasing the error, iteratively passing batches of data throughout the neural network and updating the weight and the direction with the smallest error. This is gradient descent all over again, except this time, instead of updating the weights in a single perceptron for one linear model, we're updating the weights of all the models throughout the entire neural network. Recall that even though with gradient descent we're updating the weights and moving in the direction with the smallest error, we need to do it in small steps, especially when there's a lot of data. At the moment, the lines are adjusting themselves at a very specific learning rates, which simply determines the amount by which the weights are changing at every iteration. Eventually, our neural network determines that these are the optimal weights, which will ultimately come up with a model that best classifies our data and minimizes the error. Therefore, at its root, to train a neural network, we need to minimize the error function. What is that error function? Well, remember this little thing we called cross-entropy, which was simply the average of the ln of the prediction of the blue points plus the ln of the prediction of the red points, where high cross-entropies indicate a lot of error, a bad model, whereas a low cross-entropy indicates a low error, a good model. If you don't remember what cross-entropy is, I would highly recommend revisiting the last section, but essentially, even with a deep neural network, we're still applying that same equation, we're still using that same error function. But, as you saw in the last video, to compute the prediction and the output with a deep neural network, it occurs in a feed-forward process, where the inputs traverse the entire depth of the neural network in a series of sigmoid activation functions, where eventually an output is obtained. Whereas with the single perceptron-based network, it didn't have to go through any hidden layers. But regardless of how the prediction is obtained, we're still taking the probability of all the blue points being in the positive and all the red points being in the negative region, adding them all up to obtain the total error. To recap, first we conduct a feed-forward operation on previously labeled data to obtain their prediction, where we can then apply the error function on all the probabilities to determine the total error. This error is then backpropagated in a reverse feed-forward operation to update the weights of all of our models throughout the neural network, and we keep doing that iteratively, over and over at some learning rate until we obtain a good model. How exactly does backpropagation work for a deep neural network? How exactly does backpropagation work, and how do we actually use it to train our deep neural network? Well, you may recall that I said backpropagation is simply the reverse of feed-forward. With feed-forward, we can predict the outputs for all of our training data. And now, based on the outputs of all of our data points predicted by this model, by comparing the predictions to the actual outputs of our labeled data, the more misclassifications there are, the larger the error, which more specifically is calculated with the cross-entropy formula. The average of the ln of the predictions of the points being in class 1 plus the ln of the probabilities of the points being in class 0, and just like with the single perceptron, we'll apply some form of gradient descent by taking the gradient of our error function. We mentioned that for the single-based perceptron model that the negative of the gradient takes us in the direction that minimizes the error the most. The same concept applies here. The gradient is simply the derivative of the error function with respect to all the weights in our neural network. This might seem complex, but all you need to know for this is that we use the gradient of the total error function and backpropagate it in a reverse feed-forward operation to update the weights. And we do this over and over, iteratively, over some learning rate until the resulting model is one that accurately classifies our data. That is all we're going to cover for deep neural networks. To get a sneak peek of all this, we'll go to playground.tensorflow.org, and this playground allows us to create our own neural network and see how the neural network is trained to fit some data set in real time. As you can see, there's many types of activation functions. We'll mostly make use of the ReLU and sigmoid functions throughout this course. But let's go ahead and ensure all nodes use the sigmoid function since that's the one that we're most familiar with at the moment. And we will have a learning rate of 0.03. That seems pretty reasonable. So we'll leave that. And the problem type we can simply leave as classification, since that's really all we've been dealing with, and we'll choose this circular data set. This works as well. You can go ahead and choose any set of data you want. We're going to stick with this one for now. And now the goal is to define a nonlinear boundary that separates the blue dots from the orange ones. We need a nonlinear model which best classifies this data. And to do this, we're just going to have a single hidden layer. Let's take this one off. This nonlinear model is going to be obtained from the combination of 4 linear models. Before we run this, notice how each one starts with some random model. Now if we run it through backpropagation, it's constantly updating the linear models in our hidden layer, which are then combined to form our non-linear model, which as you can see, classifies our data pretty well. You just trained a neural network and did it in real time. Now what if instead of 4 models in the hidden layer, I use 3? Let's run this. It's going to eventually train itself to form a triangular-like shape around the inner region. Let's just wait for it a little bit. Actually, I'll just fast forward this video until it does. And there you go, which makes sense because if you really think about it, if you combine these lines right here, it would indeed form a triangular region. What if we use 2 models? In this case, it's just not going to work. You could run this for however long you want. It's not going to separate these 2 regions. You can train the neural network all you want. No matter how many times it backpropagates the errors and updates the weights and biases, if you combine these lines, there is no way they will combine in a way that separates these 2 regions. You need at least 3 models or more. I found 4 to be a better choice to form a more circular decision boundary, since remember 3 was more triangular in shape. Now sometimes our data is so complex that you're going to need a lot more hidden layers with a lot more nodes. Since the more hidden layers you add, the more models you have that can combine to create even more complex nonlinear models, the deeper your neural network gets. And the deeper your neural network, the easier it is to obtain more complex models which classify very complex data sets. Eventually, if we train this neural network, it ends up classifying our data pretty well. Our desktop, Jupyter, Lab, And we'll start a new Python 3 notebook and rename this one to Deep Neural Network. Rename. And let's begin by importing numpy as np, and we'll also import matplotlib.pyplot as plt. And in our last code, we created our own set of data points with the numpy code that I asked you to copy and paste from that article. However, in this code, we will be importing a dataset directly from sklearn. sklearn provides access to many pre-prepared datasets that have a more complex geometry than the linearly separable dataset that we created earlier. We get access to all these datasets by simply, from sklearn, we're going to import datasets, thus giving us access to all sorts of datasets that we now can use. Alright, now that we've imported some relevant libraries, let's move on to importing and visualizing the specific dataset that we will be using for this section, this one right here. So what we'll do first is we will define the number of points equal to 500, and now we can access our data from sklearn. We will store our data points into the variable x while storing our label values into the variable y. We will make use of our labels in just a bit, but essentially every data point will have a corresponding label. That way we can train a model to effectively classify this data into different classes. The labels are going to be organized in a way that the larger outer circle of data points are going to be labeled as 0, and the smaller circle of data points inside the large circle corresponds to labels of 1. That's going to be our positive region, and going further from the center, we approach the negative region. And so, datasets come in many different shapes and patterns. We're going to be using this one, which we can access by calling datasets.makeCircles. We'll use the makeCircles function to access a dataset that takes the shape of 2 circles, where the larger outer circle of data points are going to be labeled as 0, and the smaller circle of data points inside the large circle will correspond to labels of 1. That's our positive region. The function takes arguments that allow us to actually customize certain properties of our dataset. The first argument represents the number of sample points. In our case, number of samples is going to equal the number of points, the variable that we define up above. In our second argument, random state is equal to, we're going to set it equal to just some random integer 1, 2, 3, and by doing so, this actually allows us to seed our number generator. By writing this line of code, it's just a way to get the same random numbers each time you run your program. That way, if there's an error in your model, we can reproduce the error every single time. Okay, and now the third argument is the noise, which refers to the standard deviation of the Gaussian noise added to the function. A large noise value will cause them to look more clustered and less organized, to deviate from their standard shape. A noise value of 0 will give you 2 perfectly circular shapes. Therefore, what we'll do is actually specify a noise value of 0.1. This will ensure that our data has some variance, and will make it more difficult for our neural network to classify the 2 datasets, ensuring that our deep neural network is being challenged properly. This lower value will also ensure that the data does not become overly convoluted, as to become very difficult to classify. We want to maintain a perfect balance. Once we actually plot our data, you can feel free to play around with this argument to visually see how it affects the deviation of our data. And the last argument, the factor, refers to the relative size of the smaller inner circle region to the larger outer circle. A factor value of 1 implies that both circles are going to be the same size. Clearly here our smaller circle has a much smaller diameter than this one. A lower factor value, such as 0.2, means that the diameter of the inner circle is 20% as large as the diameter of the outer circle, which is exactly what we have here. We will stick with the 0.2 value as it allows for optimal separation between our datasets. Once we actually run our code in just a moment, feel free to play around with these arguments to get a better visual of what I'm trying to convey. And let's go ahead and actually print x and print y before doing so. Notice how x is a 2D array of x and y coordinates, and the labels, if we scroll all the way down, are simply zeros and ones. This might not mean much to you how this is organized, but this was actually organized in a way that all the coordinates which denote points in the middle have a label of 1, and all points in the outer region will have labels of 0. So finally, after customizing our dataset as desired, we can now plot and visualize it using the familiar plot.scatter function. We can define the x and y coordinates of each labeled dataset. Let's begin with the dataset that's labeled as 0, this one right here. We must first access our dataset from our data array x, and then what we'll do is actually a Boolean check. We're going to specify grab me all the x coordinates which have a label of 0. That is, wherever y is equal to 0. For example, it seems that our first point, if I go all the way up, according to y, would correspond to a label of 0, and so we would be grabbing the x coordinate for that. It also seems like the 6th point in our x array is going to have a label of 0 as well. And so we're pretty much grabbing all the x coordinates of the points which correspond to a label of 0. And clearly all the x coordinates are in the first index of our array, the index 0. So we're selectively grabbing all x coordinates which correspond to the appropriate label. We will also plot the y coordinates of the points which correspond to labels of 0. We can do this again by accessing the dataset x, and we will do a Boolean check, y is equal to 0. However, in this case, the y coordinate of these data points will be in the second index of the data array, namely 1. And by actually plotting this, it plots the outer region. Now we need to plot all the points in the inner region, which we know correspond to labels of 1. So we simply repeat the process for the dataset labeled as 1 and copy what we had previously, except now, instead of setting the label value equal to 0, we will set it equal to 1 for both the x and y coordinates so as to grab them. And running the code, we now created a scatter plot of our data, and as you can see, this dataset will be more challenging to classify than this one. Our previous data, which we dealt with in the last section, was linearly separable, whereas this data cannot be separated by a single line. Classifying this data set will require a deeper neural network, so let's move forward to actually creating our very first deep neural network in code with Keras. If you recall, to train our neural network to come up with the perfect model, to come up with the most accurate model, we had to import a bunch of packages. Let's go ahead and delete these print statements. We know what they do. And so we will import Keras, and from keras.models, we'll import sequential, nothing new so far, and from keras.layers, we will import dense, and from keras.optimizers, we will import atom. Nothing new so far, pretty boilerplate stuff. And as before, we begin by defining our neural network as a sequential model using the sequential function. We're now going to add the input layer and the first hidden layer of our neural network. As discussed earlier, deep neural networks are useful when more complex data is being classified. A simple perceptron network is not going to be enough to classify this data. And while a perceptron network consists of an input layer and an output layer, deep neural networks make use of hidden layers in between the input and the output layers. These hidden layers simply help specify the classification of more complex data. As we discussed, they use linear combinations of simple linear perceptrons to create a network that can classify nonlinear data sets. So what we'll do is we will use model.add to add a dense network connection. We start by specifying the hidden layer, which contains 4 nodes for the circular datasets that we have. And there is technically no optimal number of nodes that you must have, but having too little nodes can drastically reduce the accuracy of your network, while having too many nodes can lead to overfitting of your data. Furthermore, as previously demonstrated in the TensorFlow playground, To form a nice circular decision boundary, we'll need to use at least 4 nodes. These 4 nodes become the first argument of the dense function, and now the second argument, the input shape, will be set equal to 2. This refers to the number of nodes in our input layer. We're only dealing with dimensions of x1 and x2. And finally, we add an activation function to our hidden layer for the nodes in our hidden layer, and we will be using the familiar sigmoid function. We've successfully defined our first layer, the hidden layer. Now we just have the final output layer to define before our deep neural network is complete. And now recall with dense, every node in the layer is connected to every node in the preceding layer. So by adding another dense network connection with the model.add function and specify a single node in this layer, ultimately what we're going to have is 2 nodes in the input layer which connect to 4 nodes in the hidden layer, which connects to 1 node in the final layer, and since this is the final layer, that's going to be the output layer. Just like we said with dense, every node in its layer is connected to every node in the preceding layer. And you can add as many layers as you want, depending on how deep you want your neural network to be, but we're going to leave everything the way it is. We will have 1 input layer with 2 nodes, 1 hidden layer with 4 nodes, and 1 output layer with a single node. I hope you can appreciate just how easy it was to specify a neural network, with an input layer, a hidden layer with 4 nodes in the hidden layer, and an output layer, all in just 2 lines of code. One of the many great things about Keras. And now the input shape parameter is not required in this call because the input layer has already been defined right here, right before the hidden layer. Although once again, we still need to add an activation function for the nodes in the output layer, and we will be using, again, the familiar sigmoid function. The structure of our deep neural network is now complete. We must now take our model and compile it, and once again we are going to be using the Atom optimizer for our network. By setting model.compile and setting the learning rate for Atom equal to 0.01, a small learning rate. And now, since our dataset only has 2 categories, just like the linearly separable dataset, we will use the binary cross entropy argument as we're only distinguishing between 2 classes, 0 and 1, 0 and 1. So we'll set the loss function equal to binary cross entropy. And now for the third argument, the metrics, we are going to be interested in the accuracy, nothing else. And as mentioned earlier, a metric is very similar to a loss function, the main difference being that the results from the loss function are actually backpropagated through the network, whereas the metric data is not used towards training the network. It acts more like a tool for the evaluation of the performance of the data. The metric accuracy essentially calculates the accuracy of how often the model's predictions match the labels of our data. And we are finally ready to train our deep neural network to come up with a model that best classifies this data. To actually train a model to fit our data, we'll use the fit function with model.fit. And what we'll do actually is we will put this in a separate cell by first running this one. We seem to have an error, and that's because I should probably run all of my cells. And we're good to go. And back to it, we will use the model.fit function to train a model to fit our data. We will first pass in the training data that will be used to train our model, x is equal to x. Then we'll be passing in the corresponding labels that we assign to each data point, y is equal to y. That way our model can distinguish as to which point should belong to which class, and thus properly training our model to separate the data. And then we will set the verbosity. Verbose is equal to 1. Again, what that will do is simply display a progress bar of information relating to the performance of our model at each epoch. Epoch simply refers to whenever it iterates over the entire data set of points, and labels to try and separate our data in discrete classes based on their assigned labels. And recall that 1 epoch is too big to feed to the computer all at once. As such, we divide it in several smaller batches. More specifically, it will be a batch size equal to 20. Since we have 500 data points in total with a batch size of 20, then it will take 25 iterations to complete 1 epoch. And at each iteration, it'll update the weights of the neural network, minimizing the error. That way it better fits the data given. And remember that the batch size really depends on the size of your data, and according to your GPU, how long it takes to process your data. A batch size of 20 in this case is a pretty good number relative to the amount of data points that we have. And alright, now how many epochs should our line go through? Obviously more than one epoch. We need to feed the full dataset through our neural network multiple times to ensure an optimized result so that it keeps updating the weights and biases of our network in the direction that decreases the error function the most. At the same time, we don't want to specify too many epochs since that can lead to the overfitting of a curve. We saw that this was a modeling error which occurs when a function is too closely fit to a limited set of data points. This is the optimum result that we need to accomplish. And so what we'll do is specify epochs is equal to 100. It will go through all of our data 100 times and no more. And now finally, remember we have to set shuffle is equal to true so as to shuffle our training data before each epoch to ensure that it doesn't get stuck in a local minimum. We want to ensure the absolute minimum of our loss function, thereby maximizing the accuracy of our model. Alright, let us train the neural network. And we seem to have an error. Y is not defined, and that is because this is not a capital Y. I keep making that mistake. Alright, and notice that at about, let's wait for it to go. Notice that at about 60 epochs, or 58 epochs I should say, we start obtaining a model that reaches 99.8% accuracy. We've successfully trained a neural network to learn how to classify this data in just a few lines of code, and it looks like we didn't actually need 100 epochs to train our data, since really it reached a maximum accuracy at about 58, 59 epochs. Again, it really just depends on what kind of data that you're dealing with. And let's actually get a visual of our neural network's progression in its training. Recall that this function over here also returns a history object. It keeps a record of the training loss and the accuracy values at every epoch, which we can get a visual of in matplotlib. And so what we'll do is we will set a variable h for history equal to the return value of our fit function. We will run this cell again, and now inside of a new cell, I'll just wait for this to finish and fast forward the video. With the pyplot subpackage plt, we will make a plot of the accuracy values which we can access from h.history. And from this history attribute, we can access all the values of our accuracy from the key ACC for accuracy. And we'll also label the horizontal axis of our plot, plot.xlabel. We will call it epoch, and we will give the plot a legend, which takes in a list, but we're only going to have one curve in our plot, which we're going to call accuracy. And let's not forget to give our plot a title as well, and that's also going to be called accuracy. Let's run our cell. This isn't really what I expected. Let me just rerun all of my cells. Run all cells. Fast forward the video until it does. And notice that this time at about 50 something epochs, our model pretty much reached maximum accuracy. So realistically, we didn't really have to do 100 epochs. Again, it really depends on the type of data that you're working with. It is also relevant to note that training our network to fit our circular data took much longer to reach maximum accuracy when compared to our previous perceptron model, where if you remember it only took 10 epochs. This can be attributed to the fact that our dataset was more complex in this specific case, requiring the network to run an increased number of epochs. Alright, so let us actually start a new cell and copy and paste this code. And instead of plotting our accuracy, we will plot the loss. We will rename our title and legend as loss as well. Run the cell. And looking at this, it seems evident that the full 100 epoch run-through was required for the loss function to fully minimize. This is actually indicative of the fact that our dataset was more difficult to classify as opposed to the linearly separable data that we dealt with in the last section. Alright, we're now going to plot our dataset along with the precise decision boundary that our model was trained to come up with. Now, plotting this along with the contour lines which specify the prediction levels in each region of our grid follows the exact same process as what we did in the last section. So instead of reinventing the wheel, I'm actually going to pull up the old code that we already worked on. We'll copy this function over to this new cell, or run this one, and we'll copy the function call along with the plot.scatter functionality as well. And one thing I want to change is instead of a tolerance of 1, let's have it be 0.25, a quarter. I found this worked better with the given data that we have. And so, according to the model that we trained to classify our data with the data points, recall that all this code did was correlate each specific coordinate with its respective prediction probability with model.predict. The function then plots distinct contour zones, each of which represent a distinct probability level, thereby actually plotting our classification boundary, the decision boundary, side by side with our data, giving us a better visual of our model. So by actually running this code, clearly we can see that our decision boundary plot effectively separates our data points into the appropriate labels. It classifies it in the sense that everything inside has a label of 1, everything outside a label of 0, and as mentioned earlier, the plot.contour function plots distinct contour zones. Each of these contour zones represent an increased threshold of probability. The dark blue zone on the very outer edge represents the lowest probability of a point being labeled as 1. This means that any point inside of this blue zone most likely has a label of 0. But now our model was trained such that the probability that a point is labeled as 1 increases as you go from the absolute blue contour zone to the absolute yellow contour zone. Any point inside of this yellow contour zone is most likely going to have a label of 1. And just like before, we are going to plot and obtain a prediction for a single chosen point. From the model that we trained to classify previously labeled data, we can now make predictions on the outputs of newly inputted data which don't have a label. So first, what we'll actually do is replot our decision boundary, just as we did before. Shift-Enter. And there seems to be some kind of print statement that I'm not too fond of. Let's remove that. Okay, clean start. And just like before, we will create an array for our point in numpy.array. And what that array is simply going to hold is the x and y values of our points. And we will specify the x value of our point as, let's say, 0.1. And we will give the y value, let's say 0.75. It's going to be somewhere over here. Y is equal to 0.75. All right, and now using the model that we trained, we can get a prediction value by feeding this point into the model.predict function. This gives us a return value of the prediction, which we will store in the prediction variable. And now let's plot our point alongside our data using the plt.plot function. We will plot its x-coordinate, its y-coordinate. It's going to have a marker of O. It's going to have an O shape, a marker size of 10, and a color equal to red as arguments. Let's also print the prediction. Prediction is prediction that we obtained from the model.predict function. And now running the code, the marked point is clearly visible among the data points that are labeled as 0. And as expected, the prediction value returned for this point is very close to 0, indicating a very low probability that this point is labeled as 1. It belongs in the class 0, and so we can conclude that our trained model made the correct prediction. It was properly trained. What if we place this point in the positive region? So we'll give it a y value of 0, so it's going to be located somewhere here. Let's try that again. And now the marked point is clearly visible among the data points that are labeled as 1. As expected, the prediction value returned for this point is close to 1, indicating a very high probability that the point is labeled 1, 99% in the positive region our point is. Congratulations, you've coded a deep neural network that's properly able to classify previously labeled data and then make predictions on newly inputted data. It's not a very deep neural network since we only have one hidden layer, but for our purposes, this worked out perfectly. But so far, all we've dealt with are binary classifications of 0 or 1. We still haven't discussed multi-class classification. I hope you guys enjoyed this lesson. Let's further expand on multi-class classification. Desktop, Jupyter, Lab. And we'll start a new Python 3 notebook and rename this one to Deep Neural Network. Rename. And let's begin by importing NumPy as NP. And we'll also import matplotlib.pyplot as PLT. And in our last code, we created our own set of data points with the NumPy code that I asked you to copy and paste from that article. However, in this code, we will be importing a dataset directly from sklearn. sklearn provides access to many pre-prepared datasets that have a more complex geometry than the linearly separable dataset that we created earlier. We get access to all these datasets by simply, from sklearn, we're going to import datasets, thus giving us access to all sorts of datasets that we now can use. Alright, now that we've imported some relevant libraries, let's move on to importing and visualizing the specific dataset that we will be using for this section, this one right here. So what we'll do first is we will define the number of points equal to 500, and now we can access our data from sklearn. We will store our data points into the variable x while storing our label values into the variable y. We will make use of our labels in just a bit, but essentially every data point will have a corresponding label. That way we can train a model to effectively classify this data into different classes. The labels are going to be organized in a way that the larger outer circle of data points are going to be labeled as 0, and the smaller circle of data points inside the large circle corresponds to labels of 1. That's going to be our positive region, and going further from the center, we approach the negative region. And so, datasets come in many different shapes and patterns. We're going to be using this one, which we can access by calling datasets.makeCircles. We'll use the makeCircles function to access a dataset that takes the shape of two circles, where the larger outer circle of data points are going to be labeled as 0, and the smaller circle of data points inside the large circle will correspond to labels of 1. That's our positive region. The function takes arguments that allow us to actually customize certain properties of our dataset. The first argument represents the number of sample points. In our case, number of samples is going to equal the number of points, the variable that we defined up above. In our second argument, random state is equal to, we're going to set it equal to just some random integer 1, 2, 3, and by doing so, this actually allows us to seed our number generator. By writing this line of code, it's just a way to get the same random numbers each time you run your program. That way, if there's an error in your model, we can reproduce the error every single time. Okay, and now the third argument is the noise, which refers to the standard deviation of the Gaussian noise added to the function. A large noise value will cause them to look more clustered and less organized, to deviate from their standard shape. A noise value of 0 will give you two perfectly circular shapes. Therefore, what we'll do is actually specify a noise value of 0.1. This will ensure that our data has some variance, and will make it more difficult for our neural network to classify the two data sets, ensuring that our deep neural network is being challenged properly. This lower value will also ensure that the data does not become overly convoluted, as to become very difficult to classify. We want to maintain a perfect balance. Once we actually plot our data, you can feel free to play around with this argument to visually see how it affects the deviation of our data. And the last argument, the factor, refers to the relative size of the smaller inner circle region to the larger outer circle. A factor value of 1 implies that both circles are going to be the same size. Clearly here our smaller circle has a much smaller diameter than this one. A lower factor value, such as 0.2, means that the diameter of the inner circle is 20% as large as the diameter of the outer circle, which is exactly what we have here. We will stick with the 0.2 value as it allows for optimal separation between our datasets. Once we actually run our code in just a moment, feel free to play around with these arguments to get a better visual of what I'm trying to convey. And let's go ahead and actually print x and print y before doing so. Notice how x is a 2D array of x and y coordinates, and the labels, if we scroll all the way down, are simply zeros and ones. This might not mean much to you how this is organized, but this was actually organized in a way that all the coordinates which denote points in the middle have a label of 1, and all points in the outer region will have labels of 0. So finally, after customizing our dataset as desired, we can now plot and visualize it using the familiar plot.scatter function. We can define the x and y coordinates of each labeled dataset. Let's begin with the dataset that's labeled as 0, this one right here. We must first access our dataset from our data array x. And then what we'll do is actually a Boolean check. We're going to specify grab me all the x coordinates which have a label of 0. That is, wherever y is equal to 0. For example, it seems that our first point, if I go all the way up, according to y, would correspond to a label of 0, and so we would be grabbing the x coordinate for that. It also seems like the 6th point in our x array is going to have a label of 0 as well. And so we're pretty much grabbing all the x coordinates of the points which correspond to a label of 0. And clearly all the x coordinates are in the first index of our array, the index 0. So we're selectively grabbing all x coordinates which correspond to the appropriate label. We will also plot the y coordinates of the points which correspond to labels of 0. We can do this again by accessing the dataset x, and we will do a Boolean check, y is equal to 0. However, in this case, the y coordinate of these data points will be in the second index of the data array, namely 1. And by actually plotting this, it plots the outer region. Now we need to plot all the points in the inner region, which we know correspond to labels of 1. So we simply repeat the process for the dataset labeled as 1 and copy what we had previously, except now, instead of setting the label value equal to 0, we will set it equal to 1 for both the x and y coordinates so as to grab them. And running the code, we now created a scatter plot of our data, and as you can see, this dataset will be more challenging to classify than this one. Our previous data, which we dealt with in the last section, was linearly separable, whereas this data cannot be separated by a single line. Classifying this data set will require a deeper neural network, so let's move forward to actually creating our very first deep neural network in code with Keras. If you recall, to train our neural network to come up with the perfect model, to come up with the most accurate model, we had to import a bunch of packages. Let's go ahead and delete these print statements. We know what they do. And so we will import Keras, and from keras.models, we'll import sequential, nothing new so far, and from keras.layers, we will import dense, and from keras.optimizers, we will import atom. Nothing new so far, pretty boilerplate stuff. And as before, we begin by defining our neural network as a sequential model using the sequential function. We're now going to add the input layer and the first hidden layer of our neural network. As discussed earlier, deep neural networks are useful when more complex data is being classified. A simple perceptron network is not going to be enough to classify this data. And while a perceptron network consists of an input layer and an output layer, deep neural networks make use of hidden layers in between the input and the output layers. These hidden layers simply help specify the classification of more complex data. As we discussed, they use linear combinations of simple linear perceptrons to create a network that can classify nonlinear data sets. So what we'll do is we will use model.add to add a dense network connection. We start by specifying the hidden layer, which contains 4 nodes for the circular data sets that we have. And there is technically no optimal number of nodes that you must have, but having too little nodes can drastically reduce the accuracy of your network, while having too many nodes can lead to overfitting of your data. Furthermore, as previously demonstrated in the TensorFlow playground, to form a nice circular decision boundary, we'll need to use at least 4 nodes. These 4 nodes become the first argument of the dense function, and now the second argument, the input shape, will be set equal to 2. This refers to the number of nodes in our input layer. We're only dealing with dimensions of x1 and x2. And finally, we add an activation function to our hidden layer for the nodes in our hidden layer, and we will be using the familiar sigmoid function. We've successfully defined our first layer, the hidden layer. Now we just have the final output layer to define before our deep neural network is complete. And now recall with dense, every node in the layer is connected to every node in the preceding layer. So by adding another dense network connection with the model.add function and specify a single node in this layer, ultimately what we're going to have is 2 nodes in the input layer which connect to 4 nodes in the hidden layer, which connects to 1 node in the final layer, and since this is the final layer, that's going to be the output layer. Just like we said with dense, every node in its layer is connected to every node in the preceding layer. And you can add as many layers as you want, depending on how deep you want your neural network to be, but we're going to leave everything the way it is. We will have 1 input layer with 2 nodes, 1 hidden layer with 4 nodes, and 1 output layer with a single node. I hope you can appreciate just how easy it was to specify a neural network, with an input layer, a hidden layer with 4 nodes in the hidden layer, and an output layer, all in just 2 lines of code. One of the many great things about Keras. And now the input shape parameter is not required in this call because the input layer has already been defined right here, right before the hidden layer. Although once again, we still need to add an activation function for the nodes in the output layer, and we will be using, again, the familiar sigmoid function. The structure of our deep neural network is now complete. We must now take our model and compile it, and once again we are going to be using the Atom optimizer for our network. By setting model.compile and setting the learning rate for Atom equal to 0.01, a small learning rate. And now, since our dataset only has 2 categories, just like the linearly separable dataset, we will use the binary cross entropy argument as we're only distinguishing between 2 classes, 0 and 1, 0 and 1. So we'll set the loss function equal to binary cross entropy. And now for the third argument, the metrics, we are going to be interested in the accuracy, nothing else. And as mentioned earlier, a metric is very similar to a loss function, the main difference being that the results from the loss function are actually backpropagated through the network, whereas the metric data is not used towards training the network. It acts more like a tool for the evaluation of the performance of the data. The metric accuracy essentially calculates the accuracy of how often the model's predictions match the labels of our data. And we are finally ready to train our deep neural network to come up with a model that best classifies this data. To actually train a model to fit our data, we'll use the fit function with model.fit. And what we'll do actually is we will put this in a separate cell by first running this one. We seem to have an error, and that's because I should probably run all of my cells. And we're good to go. And back to it, we will use the model.fit function to train a model to fit our data. We will first pass in the training data that will be used to train our model. X is equal to X, Then we'll be passing in the corresponding labels that we assign to each data point. Y is equal to Y. That way our model can distinguish as to which point should belong to which class, and thus properly training our model to separate the data. And then we will set the verbosity. Verbose is equal to 1. Again, what that will do is simply display a progress bar of information relating to the performance of our model at each epoch. Epoch simply refers to whenever it iterates over the entire data set of points, and labels to try and separate our data in discrete classes based on their assigned labels. And recall that one epoch is too big to feed to the computer all at once. As such, we divide it in several smaller batches. More specifically, it will be a batch size equal to 20. Since we have 500 data points in total with a batch size of 20, then it will take 25 iterations to complete one epoch. And at each iteration, it'll update the weights of the neural network, minimizing the error. That way it better fits the data given. And remember that the batch size really depends on the size of your data, and according to your GPU, how long it takes to process your data. A batch size of 20 in this case is a pretty good number relative to the amount of data points that we have. And alright, now how many epochs should our line go through? Obviously more than one epoch. We need to feed the full data set through our neural network multiple times to ensure an optimized result, so that it keeps updating the weights and biases of our network in the direction that decreases the error function the most. At the same time, we don't want to specify too many epochs, since that can lead to the overfitting of a curve. We saw that this was a modeling error which occurs when a function is too closely fit to a limited set of data points. This is the optimum result that we need to accomplish. And so what we'll do is specify epochs is equal to 100. It will go through all of our data 100 times and no more. And now finally, remember we have to set shuffle is equal to true, so as to shuffle our training data before each epoch to ensure that it doesn't get stuck in a local minimum. We want to ensure the absolute minimum of our loss function, thereby maximizing the accuracy of our model. Alright, let us train the neural network. And we seem to have an error. Y is not defined, and that is because this is not a capital Y. I keep making that mistake. Alright, and notice that at about, let's wait for it to go. Notice that at about 60 epochs, or 58 epochs I should say, we start obtaining a model that reaches 99.8% accuracy. We've successfully trained a neural network to learn how to classify this data in just a few lines of code. And it looks like we didn't actually need 100 epochs to train our data, since really it reached a maximum accuracy at about 58, 59 epochs. Again, it really just depends on what kind of data that you're dealing with. And let's actually get a visual of our neural network's progression in its training. Recall that this function over here also returns a history object. It keeps a record of the training loss and the accuracy values at every epoch, which we can get a visual of in matplotlib. And so what we'll do is we will set a variable h for history equal to the return value of our fit function. We will run this cell again, and now inside of a new cell, I'll just wait for this to finish and fast forward the video. With the pyplot subpackage plt, we will make a plot of the accuracy values, which we can access from h.history. And from this history attribute, we can access all the values of our accuracy from the key ACC for accuracy. And we'll also label the horizontal axis of our plot, plot.xlabel. We will call it epoch. And we will give the plot a legend, which takes in a list. But we're only going to have one curve in our plot, which we're going to call accuracy. And let's not forget to give our plot a title as well, and that's also going to be called accuracy. Let's run our cell. This isn't really what I expected. Let me just rerun all of my cells, run all cells. Fast forward the video until it does. And notice that this time at about 50 something epochs, our model pretty much reached maximum accuracy. So realistically, we didn't really have to do 100 epochs. Again, it really depends on the type of data that you're working with. It is also relevant to note that training our network to fit our circular data took much longer to reach maximum accuracy when compared to our previous perceptron model, where, if you remember, it only took 10 epochs. This can be attributed to the fact that our dataset was more complex in this specific case, requiring the network to run an increased number of epochs. Alright, so let us actually start a new cell and copy and paste this code. And instead of plotting our accuracy, we will plot the loss. We will rename our title and legend as loss as well. Run the cell. And looking at this, it seems evident that the full 100 epoch run-through was required for the loss function to fully minimize. This is actually indicative of the fact that our dataset was more difficult to classify as opposed to the linearly separable data that we dealt with in the last section. Alright, we're now going to plot our dataset along with the precise decision boundary that our model was trained to come up with. Now, plotting this along with the contour lines which specify the prediction levels in each region of our grid follows the exact same process as what we did in the last section. So instead of reinventing the wheel, I'm actually going to pull up the old code that we already worked on. We'll copy this function over to this new cell, or run this one. And we'll copy the function call along with the plot.scatter functionality as well. And one thing I want to change is, instead of a tolerance of 1, let's have it be 0.25, a quarter. I found this worked better with the given data that we have. And so, according to the model that we trained to classify our data with the data points, recall that all this code did was correlate each specific coordinate with its respective prediction probability with model.predict. The function then plots distinct contour zones, each of which represent a distinct probability level, thereby actually plotting our classification boundary, the decision boundary, side by side with our data, giving us a better visual of our model. So by actually running this code, clearly we can see that our decision boundary plot effectively separates our data points into the appropriate labels. It classifies it in the sense that everything inside has a label of 1, everything outside a label of 0, and as mentioned earlier, the plot.contour function plots distinct contour zones. Each of these contour zones represent an increased threshold of probability. The dark blue zone on the very outer edge represents the lowest probability of a point being labeled as 1. This means that any point inside of this blue zone most likely has a label of 0. But now our model was trained such that the probability that a point is labeled as 1 increases as you go from the absolute blue contour zone to the absolute yellow contour zone. Any point inside of this yellow contour zone is most likely going to have a label of 1. And just like before, we are going to plot and obtain a prediction for a single chosen point. From the model that we trained to classify previously labeled data, we can now make predictions on the outputs of newly inputted data which don't have a label. So first, what we'll actually do is replot our decision boundary, just as we did before. Shift-Enter. And there seems to be some kind of print statement that I'm not too fond of. Let's remove that. Okay, clean start. And just like before, we will create an array for our point, numpy.array. And what that array is simply going to hold is the x and y values of our points. And we will specify the x value of our point as, let's say, 0.1. And we will give the y value, let's say 0.75. It's going to be somewhere over here. Y is equal to 0.75. All right, and now using the model that we trained, we can get a prediction value by feeding this point into the model.predict function. This gives us a return value of the prediction, which we will store in the prediction variable. And now let's plot our point alongside our data using the plt.plot function. We will plot its x-coordinate, its y-coordinate. It's going to have a marker of O. It's going to have an O shape, a marker size of 10, and a color equal to red as arguments. Let's also print the prediction. Prediction is prediction that we obtained from the model.predict function. And now running the code, the marked point is clearly visible among the data points that are labeled as 0. And as expected, the prediction value returned for this point is very close to 0, indicating a very low probability that this point is labeled as 1. It belongs in the class 0, and so we can conclude that our trained model made the correct prediction. It was properly trained. What if we place this point in the positive region? So we'll give it a y value of 0, so it's going to be located somewhere here. Let's try that again. And now the marked point is clearly visible among the data points that are labeled as 1. As expected, the prediction value returned for this point is close to 1, indicating a very high probability that the point is labeled 1. 99% in the positive region our point is. Congratulations, you've coded a deep neural network that's properly able to classify previously labeled data and then make predictions on newly inputted data. It's not a very deep neural network since we only have one hidden layer, but for our purposes, this worked out perfectly. But so far, all we've dealt with are binary classifications of 0 or 1. We still haven't discussed multi-class classification. I hope you guys enjoyed this lesson. Cross-entropy is a method of measuring error within a neural network, and consequently a lower cross-entropy value implies a more accurate system, while a higher cross-entropy value implies a less accurate system. The previous formula that we discovered for cross-entropy was the following. This formula applies to a binary dataset, where we have some number of points m. Recall that ultimately, what this equation did was take the ln of the probability of the points being in the positive region, which was then added to the ln of the probability of the points being in the negative region. We did that for every single point, then took the negative to obtain the total cross-entropy. If you're not familiar with this equation, make sure to refer back to the neural network section since we've implemented it into our code. Anyways, the larger the cross-entropy value, the larger the error, the less accurate our model was, and vice versa. Multi-class cross-entropy functions the same way, in the sense that it still provides us a tool for measuring the performance of our network. The same concept applies even if we're dealing with many classes. The larger cross-entropy, the larger the error. Let us refer back to our sports ball type example to help explain just how multi-class cross-entropy is calculated. You first begin with a certain number of data points. For this example, let's choose 3 arbitrary data points. Let's assume we have 3 unidentified balls, each one with some input of size, weight, color, and texture. What we'll do is pass the inputs of each ball into our neural network. First, we pass in the inputs of the soccer ball, and the neural network determines it has a 40% probability of it being a soccer ball, a 20% probability of it being a basketball, and a 40% chance of it being a volleyball, which isn't very accurate. Then we pass in the inputs of the basketball, and the neural network determines it has a 30% chance of being a soccer ball, a 60% chance of being a basketball, and a 10% chance of being a volleyball. This prediction is somewhat accurate since it assigns the higher likeliness towards it being a basketball. And finally, the volleyball, passing its inputs into the neural network. The neural network predicts its likeliness of it being 50% a soccer ball, 30% a basketball, and 20% a volleyball. Let's plot our results onto a table. These are just tabulated values that the neural network predicted. Now ball 1, ball 2, and ball 3 have already been labeled. They've already been one-hot encoded as being a soccer ball, basketball, or volleyball. Although our neural network, the current model, predicts that ball 1 only has a 40% chance of being a soccer ball, ball 2 only has a 60% chance of being a basketball, and ball 3 a 20% chance of being a volleyball. Clearly the current neural network is inaccurate. The model misclassified our data. Whatever model we're using, it has a large error. We must calculate the total error and thus calculate the cross-entropy for this specific set of data. Just like how we did it for binary classification, we simply take the natural logarithm of the probability of each data sample being what it actually is. Our first ball, which is already labeled as a soccer ball, its probability of actually being a soccer ball according to our neural network is 0.4. So we'll take the ln of that. Our second ball, already labeled as a basketball, its predicted probability of actually being a basketball according to our neural network is 0.6. So we'll take the ln of that and do the same thing for the labeled volleyball. We'll take the ln of 0.2, the ln of the prediction of it actually being a volleyball according to our model. We'll add everything up, and don't forget we always take the negative and thus obtain a cross-entropy of 3.04. And just like before, the higher the cross-entropy value, the higher the error. This is very similar to how we did it for binary classification, except now instead of using binary cross-entropy, we're making use of categorical cross-entropy. This was our equation for binary cross-entropy. Our categorical cross-entropy equation is a little bit different. Having calculated the cross-entropy for this set of data, let's actually generalize categorical cross-entropy into an actual formula like we did here for binary. What we'll do is first convert our probabilities into variables. The variables here represent the events, the predictions made by the neural network on each ball being a soccer ball, a basketball, or a volleyball. In order to calculate a general formula for the cross-entropy, we must recognize the steps we took to calculate the cross-entropy in our specific case above. We'll represent the row as I and the columns j. This makes sense if you think of this as a matrix with the rows and columns. The axis traversing the rows is often denoted as I, whereas the axis traversing the columns is often denoted as j. Anyways, we add the ln of each prediction in all of the cells in the first columns, and multiply each row by the event of whether or not something is true. An event that's true will have a value of 1, while an event that does not occur will have a value of 0. So if we were to draw another table, we'd end up with the following. The first ball is already labeled as a soccer ball. It's been one-hot encoded as a soccer ball, such that it has a value of 1, 0, 0. The first event is true, it does occur. We know this ball is a soccer ball, it's not a basketball or a volleyball. This one is not a soccer ball, nor is it a volleyball, this one is a basketball, so it's one-hot encoded as 0, 1, 0, and the same concept applies to the volleyball. It's one-hot encoded as 0, 0, 1. So what we do is we take the ln of each prediction, multiply it by the event of it occurring or not, giving us the cross-entropy for a single ball. But notice the other two values cancel out, which is exactly the point. Thanks to the one-hot encoded label, it cancels out two cells, and for the first ball, takes the probability of the ball being what it actually is. Then we do the same thing for the second column. Notice the first and third value cancels out, thus only taking the ln of the probability of the second ball being what it actually is, a basketball. And the same thing for the third column. The first and second value cancel out, and then we end up adding everything up along the axis I. The next step is to then take the negative and thus obtaining the total cross-entropy. We know P11 was initially 0.4, P22 was 0.6, P33 was initially 0.2, and would you look at that, we get the same equation as before with the same result, 3.04. And that will be the formula for multi-class cross-entropy. As mentioned earlier, the smaller the cross-entropy value, the better the model, so we then use some sort of gradient descent algorithm to minimize the error obtained. It is also important to mention that the process of gradient descent and the process of backpropagation are both not generally affected by shifting the analysis of a binary dataset to a multi-class dataset. We're still trying to minimize the error by updating our linear parameters based on the gradient of our error function. Nothing changed. Having discussed the main differences that must be considered when analyzing a binary dataset versus a multi-class dataset, we are finally ready to move forward towards classifying our first multi-class dataset with Keras. I look forward to seeing you there. Any more complex deep neural network. However, both of these networks were similar in the sense that they were designed to separate a dataset containing only two labels, 0 or 1. While the perceptron model dealt with linearly separable data, our deep neural network dealt with the separation of a more complex dataset. In this section, we'll take this one step further by discussing multi-class datasets and the theory associated with these datasets. We'll then implement this into code by separating our data into 3 classes. The term multi-class dataset simply refers to datasets that contain more than 2 data classes. This means that 3 or more labels are present in the dataset, whereas before, we had only dealt with datasets that had 2 labels, 0 or 1. This introduces brand new obstacles for data classification. The first crucial difference we face between dealing with binary datasets as opposed to dealing with multi-class datasets is the replacement of the sigmoid activation function. As discussed earlier, the sigmoid function is a very useful tool to use for classifying binary datasets. It ranges in probability values between 0 and 1. The predicted probability of a point being 0 as it infinitely approaches the negative region of a model, and reaching close to 1 as it approaches positive infinity. And as you saw, takes the form of the following equation, which converts the variable x, the score of a point, to a probability. This is nothing new, we've already covered this in the last 3 sections. These properties of the sigmoid activation function make it an ideal candidate to be used for classifying binary datasets. However, it is not feasible to use this model for multi-class dataset classification. Its span limitation between 0 and 1 makes this difficult. So here we introduce a new activation function that is capable of dealing with multi-class data. That is the softmax function. The softmax function is a useful activation function for scenarios involving multi-class functions. And before we fully jump into the workings of the softmax function, let's take a look at an example of a multi-class dataset to better understand how these datasets are processed through our neural network. Imagine you are designing a neural network that is capable of distinguishing between different types of sports balls. The network should be able to distinguish between a soccer ball, a basketball, and a volleyball. As there are 3 distinct classes to identify, it can be seen that this is a multi-class data set. Now, in the process of identifying these objects, the network must first take some inputs from the object that is to be identified. This can include things such as weight, texture, color, and size. After these inputs are fed into the neural network, they are manipulated by the weights and bias values of the connections between the input layer and the output layer. Notice how there are 3 output layers, since we're dealing with 3 mutually exclusive classifications. We'll look more into the outputs momentarily, but just think of how previously we only dealt with a single output layer, which simply returned the probability of a point being in the positive region or not, 0 or 1. However, with multi-class classification, suppose we passed in the inputs x1, x2, x3, and x4, which relate to weight, texture, color, and size of some random ball, and we fed it into our neural network through some feed-forward operation. This manipulation eventually returns some score value for each of the ball types. Since there are 3 outputs, we end up with 3 scores. So let's assume after passing our inputs throughout the entire depth of the neural network, as the inputs are constantly being combined through the weights and biases of our network, eventually the network outputs 3 scores, such that the chances of our ball being a soccer ball gets a score of 2, the basketball gets a score of 1, and finally the volleyball gets a score of 0. These scores are nice to have, I guess, but I don't know about you, they don't really mean anything to me. Unless I'm able to convert these scores into probabilities, in order to make these values practical to use for a prediction. The first important thing to consider during this conversion is that the relative magnitudes of the scores must be maintained. This means that a score of 2 must have a higher probability than a score of 1, and similarly so when comparing a score of 1 to a score of 0. That being said, it's clear that by looking at these scores, the inputs of the random ball that we passed into our neural network most likely corresponds to that of a soccer ball. Alright, so the first big condition is that the relative magnitudes must be maintained. The second thing is to remember that all probability values must add up to 1. Both of these requirements can be satisfied using the softmax activation function. That's exactly why, for multi-class classification, we must use the softmax function as it satisfies the two conditions. The softmax function has the following equation. This equation refers to the probability of some score m when there are n number of classes present in the data sets. So what you would do is for each score m, e to the m is divided by the summation of the exponential of all scores, namely e to the m divided by e to the 1 plus e to the 2 plus e to the 0. This equation ensures that the relative magnitude of the scores is maintained, and also ensures that all output probabilities sum to 1 as required. To get a better visual at this, in our particular case, if we sub the numbers into the softmax function, to obtain the probability of our ball being a soccer ball, sub in the score e to the 2, and divided by the exponential summation of all other scores, e to the 2 divided by e to the 2 plus e to the 1 plus e to the 0, which results in a value of 0.67. We do the same thing for the probability of the point being a basketball. E to the 1 divided by e to the 2 plus e to the 1 plus e to the 0, which returns a 0.24 probability of the ball being a basketball, and finally doing the same thing for the volleyball results in a probability of 0.09. Therefore, the inputs, the attributes of the ball we passed into our neural network, result in scores of 2, 1, and 0 after being multiplied and combined through various bias and weight values of our network. And then, that's where we apply the softmax function. We apply it to our final layer, which then determines probabilities of a 67% chance of the ball being a soccer ball, 24% chance of the ball being a basketball, and a 9% chance of it being a volleyball. Therefore, our ball is more likely to be a soccer ball than anything else. Alright, we have now found an appropriate activation function that deals well with the classification of multi-class data. The feed-forward process to determine the probability of something being what it is very similar to how we did it for binary classification. We're passing our input nodes through activation functions in every node of every hidden layer, except now this time, in the output layer, we have to make use of the softmax function to convert our final scores to probabilities. We are able to make probability predictions on newly inputted data. However, recall that to make predictions on newly inputted data, first we have to train the neural network. And since we're dealing with a supervised learning algorithm, we're training the neural network based on previously labeled data. We have to make use of datasets which already have discrete labels of being a soccer ball, a basketball, or a volleyball. However, there is just one problem. Our training data, how do we actually label it? With binary classification, we simply had labels of either 0 or 1, and there were no issues of dependence among the two labels. Although, transferring from binary datasets to multi-class datasets also presents another issue. With multi-class datasets, we cannot follow the same procedure. In the case of this example, our intuition would tell us to label these classes from 0 to 2, such as labeling a soccer ball as 2, a basketball as 1, and the volleyball as 0. This seems like a concrete solution. However, the issue with this solution is that it assumes dependency between the classes. This is what's known as label encodings, which gives numerical aliases to different classes. The problem with this, label encoding assumes some kind of relation, some kind of dependence between our classes, such that our algorithm might consider these to be in some kind of order, 0 to 1 to 2, which doesn't make any sense. These classes are mutually exclusive. We don't want the algorithm to consider one class more highly ordered than the other, or process the classes with any sort of favoritism. For this reason, we cannot use label encoding. To label our training data, we use one-hot encoding. One-hot encoding allows us to classify all of our classes without assuming any dependence between the classes. One-hot encoding works by creating separate columns for each data label in the data sets and using an appropriate 1 or 0 value for each column to identify the data class. For our data, this would look like the following table. Since we're dealing with 3 classes, we create 3 columns. The presence of a class is presented in binary format, If something is a soccer ball, it will be 1 hot encoded as 100. If it's a basketball, it's 1 hot encoded as 010. If it's a volleyball, 001. As you can see, this technique allows us to create independent labels for each of our data classes and ensures that our data does not assume any relation between our classes. They're linearly independent. This can be done for any number of classes using the appropriate number of columns. Now we have gained another tool to use for classifying multi-class datasets using neural networks. Alright, so the process is similar to how we did it with binary classification. We're training a neural network based on previously labeled data which are 1 hot encoded. Using that labeled data to train our network to develop the perfect model and classifying it by updating the weights and biases of our network through some gradient descent algorithm. And then using that model, we can make predictions on newly inputted data which don't have a label and predict their probability with the softmax function of it belonging to one of the 3 classes. That is the grand scheme of things. Now that we have dealt with the logistics of data organization and data score analysis, let's begin to discuss how the process of deep learning changes when we go from a binary dataset to a multi-class dataset. I'm going to design a basic neural network to categorize this multi-class dataset and evaluate its performance to validate our design. As usual, you'll have to open up a new Jupyter notebook. I've already gone ahead and done that. And once you do, let's begin by importing the relevant libraries. We will import NumPy as NP. And next we will import matplotlib.pyplot as PLT. For this section of the course, we will once again be importing a dataset from sklearn. And to get access to all these datasets, we can do that by simply importing datasets. As we will be building another neural network in this section of this course, we can also simply import the relevant Keras libraries as well. And so from keras.models, we can simply import sequential, allowing us to define our neural model. And from keras.layers, we can import dense, the dense layer. As mentioned earlier, the dense layer allows us to connect preceding layers in the network to subsequent layers. We have used this layer type previously, and we will continue to do so in this section. And now finally, from keras.optimizers, let's import our familiar optimizer Atom. That is all for the boilerplate configuration. Let's move on to the fun stuff, importing our very first multi-class data sets. Let us first define the number of points, and the number of data points, n points is equal to 500. And now we can import our data set from sklearn. Recall sklearn provides a variety of data sets to pick from. These data sets come in many different shapes and patterns. This time we will be using the dataset.makeBlobs pattern. This one is pretty self-explanatory. It makes blobs in different coordinates of the grid. We'll be using this function to import a data set. This function creates a cluster of data points that are all randomly centered around a chosen central point for the cluster. We can also choose just how many of these clusters we want, and we can choose the central location at which we want to place each specific cluster. Before we can call the dataset.makeBlobs function, we need to create a nested list that specifies the coordinates of the center of our clusters. Let's call this list centers and define the 3 central coordinates for our clusters. This will allow us to have 3 distinct data classes, each defined by its respective cluster data set. And now let's center our first cluster on the -1 and 1 coordinates. Our second cluster will be centered on the point, let's say -1 and -1. And finally, our last cluster will be centered on the point 1 and -1. The exact positions of these centers is not too important. However, these specific positions were chosen to create a small degree of separation between the data classes so that they can be effectively classified. This will be more clear once we actually run the code and you can see a visual of how the data is separate. Anyways, we will now create our data set and store our data points inside of the variable x like we always have done it, and we will store our label values into the variable y. We'll make use of our labels in just a bit, but essentially every data point will have its corresponding label. That way we can train a model to effectively classify the data into different classes, according to the label that it belongs to. We then call dataset.makeBlobs, and we'll feed it the appropriate arguments to create our multi-class dataset. The first argument represents the number of sample points. In our case, number of samples is just going to equal our number of points. Our second argument, random state, we're going to set it equal to just some random integer, 1, 2, 3, and by doing so, this allows us to seed our number generator. That way we can get the same random data sets each time you run the program. That way if there's an error in your model, we can reproduce the error every time. And if you want consistent results as myself, make sure to use the same seed. The third argument, centers, essentially asks for data referring to the center point of each of our clusters. This is where we refer back to the nested list we created above called centers, like so. The list contains a total of 3 two-dimensional coordinates that indicate the center point of the data clusters that we want to create. And for this reason, it was important to generate these coordinates prior to generating our data set. And so the final argument, cluster std, refers to the standard deviation of the clustered points around their respective centers. A value of 0 would cause all the points to be generated precisely at the chosen center coordinate of the cluster. As this value increases, the generated data points deviate further and further away from their chosen center point. Therefore, we are going to pick a reasonable value of 0.4, like so. This value will allow us to balance between clusters that are too dense and easily separable versus clusters that are too widespread and overlapped. We can now visualize the data we have created to gain better insight on what multi-class datasets really look like on the scatter plot. So before doing so, let's go ahead and print x and print y. And we seem to have an error. Name dataset is not defined. That is because we should be using datasets, not dataset. Let's try this again. All right. Notice how x, as you know, is a 2D array of x and y coordinates. And the labels, this time, since we're dealing with 3 classes, the labels are 0, 1s, and 2s, representing our 3 different mutually exclusive classes. Just copy and paste this real quick over here. And the data sets are arranged in such a way that the data set centered at -1, 1 has a label of 0. So clearly we know that the 4th coordinate inside of the X array is part of this cluster. Just a simple example. And the data set centered at -1, -1 has a label of 1, and subsequently the cluster at coordinate 1, -1 will have label of 2 for every single point that's inside of it. So finally, after customizing our data set as desired, we can now plot and visualize it using the familiar plot.scatter function. We can now define the x and y coordinates of each labeled data sets. Let's begin with the data set labeled 0. We must first access our data set, and then we'll do a Boolean check. That is, grab me all the x coordinates which correspond to labels of 0, where the corresponding label equals 0, and clearly all the x coordinates are in the first index of our array. We'll do the same exact thing for the corresponding y coordinates. Let's just copy that. And we know the y coordinates are in the second index. Okay, by plotting this, what it does is it plots the cluster of data that's centered at -1 and 1. Now we need to plot all the points in the other clusters, which we know correspond to labels of 1 and 2. So we repeat this process. Let me just copy and paste those. We'll set a label of 1 here. That way it grabs all the points which correspond to labels of 1, that is, the cluster of points that correspond to these labels, and we will do the same thing for the cluster of points that correspond to labels of 2, thus grabbing all the points with labels 1 and 2, and by running the code, we've now created our scatter plot of data, and the multi-class element of our data can clearly be seen. 3 distinct classes are shown, whereas before this section we only dealt with 2 data classes. Now that we've successfully created and plotted our data, we need to pre-process it appropriately. The dataset is already well organized. However, our label data needs to go through the hot encoding process. We already talked about this in the theory section. But anyways, as discussed earlier, this process eliminates unnecessary dependencies within our data labels and ensures that our neural network does not create unjustified relationships between our data labels. In order to see this hot encoding in action, let's actually print our Y label over here, simply to see what the labels look like before the hot encoding process. We know it's simply a one-dimensional array which consists of numbers from 0 to 2. Each of these numbers refers to a label of a specific data point within our data. The label 2 corresponds to the cluster of data 1, -1, if you remember. The label of 1 corresponded to the cluster of data -1, -1, and accordingly 0 at this cluster of data right here. Alright, so let's move forward and begin the hot encoding process. This process begins by first going upstairs, and let's eliminate that. What we'll do is first from keras.utils.np_utils, what we're going to do is we will import toCategorical. You'll see what that is in a bit. toCategorical, make sure I spelled that right. What that does is it allows us to make a call to the toCategorical function, which takes our dataset labels as inputs, reformats them, and outputs them in a one-hot encoded form. So now that we've imported toCategorical, let's put it to use. We will define a variable, ycat, as in yCategorical, to store our newly hot encoded data. Now we call toCategorical, which takes the following 2 arguments. So the first argument is going to be y, which contains the labels for our dataset points, the labels which we have to hot encode. The second argument is actually optional, and is simply going to be an integer value that represents the amount of data classes that we have in our data set. If this argument is left blank, this function is simply fed the default, which is 3 data classes. If more than 3 data classes are used in the data set, the specific number must be written as the second argument inside of toCategorical. So you know what, we will specify it anyway. And to help visualize the one-hot encoding process, let us print our new dataset ycat and see how our data arrangement has changed. We seem to have made an error, and that is, I forgot to run this first cell. Or you know what, let's just run all cells for the sake of it. And there you go. So clearly ycat is a 2-dimensional array that is 500 rows by 3 columns. Each row corresponds to the label of 1 data point. Each row contains a hot encoded value for the labels that we printed out with the print_y statement. The labels that were previously 0 have been replaced with a row of values with the sequence of 1, 0, 0. Similarly, the values that were previously 1 and 2 were replaced with a sequence of 0, 1, 0 and 0, 0, 1 respectively. Seeing these visual outputs helps to understand just what this hot encoding process is doing and how it functions to allow us to classify all our data classes without assuming any dependence between them. Alright, so that is one-hot encoding in a nutshell. Alright, and if you're not too sure why we're doing one-hot encoding, I strongly suggest you refer back to the last lesson. We discussed it in a lot of depth. And so now let's actually design the neural network that we will use to classify our multi-class data sets. It's just going to be a simple perceptron network with an input layer and an output layer. No hidden layers this time will be used, as they are not necessary for classifying this data set. A deep learning neural network will be used in the next section of this course to classify a more complex multi-class data set known as the MNIST dataset. However, for the purposes of this section, we are going to design a more simple neural network to understand the basics of multi-class dataset classification. Alright, so as before, we begin by defining our neural network as a sequential model which uses the sequential function. We then add the input layer and the output layer. Having defined the sequential model, we can now start adding layers to the structure, and as mentioned earlier, we are going to create a simple neural network with 1 input layer and 1 output layer. And since the data points are defined by a simple Cartesian coordinate system, an x and a y coordinate, our input layer is only going to have two input nodes, because you can also think of this as x1 and x2. And as for the output layer, since we have three distinct data classes in our multi-class data set, we are going to need three nodes on the output layer to effectively classify our data. So back to here, what we'll do is using the model.add function, we can begin to add layers to our network in the first argument. Inside the argument, we'll specify the properties of our dense layer. The first argument units, which we're just going to have as 3. Since this is the first layer being created, we must also define a number of input nodes. This is done through the second argument, the input shape, which is simply going to equal 2. We're only going to have 2 input nodes. And now the final argument, the activation, defines the activation function using the output layer nodes of the network. And as mentioned earlier, for multi-class data classification, the sigmoid activation function is not sufficient. We must make use of the softmax function. So this time our activation function instead is going to be called softmax accordingly. And this function is able to effectively classify multi-class data. And now before training our model, we need to configure the learning process, which is done via the compile method. What we need to do is specify what kind of optimizer we're going to use, what kind of error function, and the metrics. The optimizer we'll use is Atom with a learning rate of 0.1. Our loss function will equal some form of cross entropy. As you know, the loss function will help us determine the error. Since we're dealing with a multi-class data set, we'll be using the categorical cross entropy. Make sure you don't capitalize anything. And this calculates the cross entropy value for multi-class data set classification problems. And as for the metrics, we'll need to calculate the accuracy of our model. So we'll just set it equal to accuracy, a list of only one element, since all we want to do is calculate the accuracy of the model's predictions, which match the labels of our data. And once again, to actually train a model to fit our data, let's just run this cell for now. And what we'll do is we will use the model.fit function yet again to train our data. We'll first pass in the training data that will be used to train our model. X is equal to X. Then we'll be passing in the labels that we assign to each data point. Y is equal to Y categorical. And now notice that these are the same labels that we previously hot encoded. This is a very important distinction to make because the compile process requires that the labels are hot encoded. Hot encoding these labels is what allows the compilers to actually compare the output of the neural network to the expected label for any specific data point. That way it can determine the proper error. The theory behind the importance of hot encoding is discussed earlier in this course, but the distinction is made here to demonstrate the importance of the hot encoding process. Once again, we'll just set the verbosity. Verbose is equal to 1 to display a progress bar of information relating to the performance of our model at each epoch. And now we'll set a batch size equal to 50. Since we have 500 data points with a batch size of 50, then it will take 10 iterations to complete one epoch. So taking 10 iterations for it to process all of our data, updating the weights of our neural network, minimizing its error through gradient descent. And recall the batch size really just depends on the size of your data. And according to the GPU, how long it takes to process your data. A batch size of 50 is a pretty good number considering how many points we have. And how many epochs? We don't really want to specify an insufficient number of epochs since that can lead to the underfitting of the curve, which doesn't capture the underlying trend of data. At the same time, you don't want to pass in too many epochs since that can lead to overfitting, a modeling error that occurs when a function is too closely fit to a limited set of data points. Really, it's hard to tell how many epochs you need until you train the model and see how many epochs it took for it to reach maximum accuracy. So there really isn't a right answer, it just depends on your data set. What we'll do is specify epochs is equal to 100. It'll go through our data 100 times, no more. All right, let us actually just run this code and train a model. And it is training the model, and clearly at about not even 25 epochs, or 20, let's go back down here. Not even at 2 epochs, it already reached maximum accuracy, so we didn't really need 100, but regardless, let us now plot our data set along with the precise decision boundary that our model was trained to come up with. Now plotting this along with contour lines follow a similar process from earlier, so instead of reinventing the wheel, we'll reuse the code from our single perceptron-based model project. If you don't have the project, don't worry too much about that. I've left the code for you in the previous article. But regardless, let's just copy and paste this function that we already came up with. And let's also copy and paste the function call. Let's run that. There you go. And one thing I want to change is instead of y, this will be y categorical. And we will fix it in our function accordingly wherever it says y. And we'll fix it in our function call accordingly so as to properly denote the one-hot encoded labels. And looking back at this, it looks like we were never actually using the labels inside of our function. But you know what, we'll just keep this for now. And remember, all this function does is draw contour zones according to the decision boundary obtained from our network, the most accurate model that classifies our data. If you're not sure how this function operates, I would highly recommend revisiting the first code we did with Keras. But anyway, there's just one tiny thing we have to change, and that is instead of model.predict, we'll use the model.predict classes function with grid as the sole argument. This function is slightly different than the previous model.predict function we used to create predictions for a binary datasets. The model.predict classes function is specifically for datasets that are multi-class such as ours. By feeding the entire grid array into model.predict classes, the trained model that we developed tests all the points inside our grid. It's going to test all of these points and return an array of predictions. What it's going to do is look at the data obtained from the training of our neural model and uses it to classify the class of each of the data points of the grid that we created. And the final role of our plot decision boundary function is to create a contour plot of our predicted results using the plot.contourf function. The function then plots distinct contour zones, this time each of which represents a distinct class zone. Before, each contour zone represented a certain probability level, but now each one represents a distinct class zone. Keep this in mind. It will be explained further in detail after we see the resulting plot. Alright, now along with plotting our decision boundary, let's also plot our data to get a better visual understanding of how the decision boundary separates our labeled data. And so what we're actually going to do is, instead of redeclaring this, let's just copy and paste that over here. Run the code, and we have an error. Cannot reshape array of size 7500 into shape 5050. That's kind of an odd error. I'm just going to run all of my cells and see if there was just something we forgot to run. Alright, everything works out fine. And this is pretty cool. We can see that our decision boundary contour plot effectively separates our data points into their appropriate labels. And as mentioned earlier, the plot.contourf function plots distinct contour zones. Each of these contour zones represent a distinct data class. To understand how these zones are constructed, we need to go back to the training process for our neural network. During the training process, at every single epoch, the network is fed inputs that are manipulated by the weights and biases in our system and are then fed as score values into the nodes found on the output layer. In our case, there are 3 output nodes. Each node corresponds to a specific class within our data set. After the scores are fed into the 3 nodes, they are fed through the softmax activation function and then outputted as probabilities. The node that outputs the highest of the 3 probabilities indicates that the input that was fed into the neural network has a label associated with its respective data class. As an example, assuming that the uppermost node in the output layer was associated with the data class labeled 0, If the uppermost node returned the highest probability of the 3 nodes, then it indicates that the input data point was associated with the class that is labeled as 0. Now, after our dataset has been trained to accurately classify specific data points with specific data classes using the process described above, the contour maps can be created. The contour map then shows differently colored regions that correspond to the different data classes that we have. In our case, the purple zone is associated with the class labeled 0. The green zone is associated with the class labeled 1. And finally, the yellow zone is associated with the class labeled 2. What this means in a basic sense is that if an input point lies in a specific colored zone, then it is classified as belonging to the class associated with that zone. The specific shape of these zones is determined directly through analysis of our data. We are now going to learn how to plot and obtain a prediction for a single chosen point. So what we'll do is actually replot our data in decision boundary as we did before. And now we decide the coordinates for our test point. We'll define a point with horizontal coordinate at 0.5 and y is equal to 0.5, somewhere in this vicinity. So what we'll do is create a point array is equal to numpy.array. This will contain our x and y coordinates, x and y, and recall we wanted x to be 0.5 and y was going to be 0.5 as well. Now we can obtain a prediction value by feeding this array into model.predict classes, and we will predict the class for the points. All right, now let's plot this point alongside our data. plt.plot. We will plot it at the specified x coordinates. Plotting it at the specified y coordinates, we'll give it a marker equal to an O shape with a marker size of 10, and let's say a color of, let's say red, R for red. Let's also print the prediction. Prediction is the prediction itself. And turns out I forgot to actually set prediction equal to the return value of model.predict classes. Let's output the code. And there you have it. It is labeled as 0. Why is that? Well, recall anything in this cluster of data was identified as having a label of 0. And what happened was, since this point is closest to being in this region, if we think in terms of our perceptron, the node that outputted the highest of the 3 probabilities was the node that was associated with the class that is labeled 0. If I just move this point a little bit below its position, let's say at 0.5 and -1, then the prediction is 2, which makes sense since it is inside the class which is defined to have a label of 2. So thinking in terms of the neural network, the node that outputted the highest probability was the node associated with this single class. And there you have it. We've successfully classified our first multi-class data set. Our dataset consisted of 3 distinct data classes and was relatively easy to classify. However, it would be interesting to see how effectively this classifying process works when we have more than 3 classes. Let's revisit our code and make this a reality. The first step in this process is to actually create more classes to begin with. So we must first revisit our list over here we created earlier, the centers. The centers of our first 3 data classes are already defined. So what we'll do is add 2 more center points for the 2 new data classes we're about to create. We're going to center 2 new data sets on the points 1 and 1, and on the points 0 and 0. Our centers list should now have 5 entries, including the initial centers that we had previously that are right here. And next, in this cell, what we can do is add some more scatter plots to visualize our new data set. We simply copy and paste the following. And now, instead of 2, we will put 3 and 4 here. These statements will scatter new data that has already been labeled as 3 and 4 respectively by the datasets.makeblobs function. So let's actually run this cell. And we run this one. And as you can see, we have created 2 more data classes to our data. And our data set looks a bit more complex now. The addition of our 2 data classes means that we have to reflect this change in the structure of our network. This change is mainly reflected in the number of nodes in the output layer. Since we have 2 more data classes, we need to add 2 more output nodes. And this can be done in the model.add statements inside the dense function. And once again, we will need to go back here and plot the additional data points. Let's plot the points associated with labels of 3 and plotting the points associated with labels of 4. Copy and paste the following here as well. All right, and what we actually need to do is retrain our model to fit this new set of data. So just to be safe, let's run all of our cells. We seem to have an error. Index 3 is out of bounds for axis 1 with size 3. And that is because in this argument, we have to specify how many classes we're dealing with. In this case, we're dealing with 5. Let's rerun all of our cells. This seems like it's still training. And all right. As you can see, the geometry of these maps has shifted to accommodate our new data sets. The network does a reasonably good job at classifying our data points, with some exceptions. This is expected considering that our data is quite complex and densely packed, which causes overlapping among the classes. What is important to note, however, is the fact that these neural networks are a very powerful tool and they are capable of classifying very complex and diverse data sets. Now let's move forward towards creating a deep neural network for classifying a complex multi-class data sets, namely the MNIST data sets.